You're listening to the Breadcrumb Mojito podcast, hosted by Connor Whale.
That's not bad.
No, exactly. We're doing good.
Yeah.
Marvelous. Oh, Cairan, thank you
Connor.
very much for coming on and having a chat with us today.
That's okay. I'm excited.
I'm very excited. I have been looking forward to this all week.
Okay, cool. Yeah, I've been looking forward to it with anxiety.
Why so anxious?
I don't know. I'm sure it'll be fine.
Yeah, it'll be fun. It'll be fun. As I was really interested because I speak to so many hospitality people that it is a nice chance to sort of break up the common cycle that I talk about constantly, and an opportunity to learn something a little bit new.
Yeah, let's do that.
Okay,
I think that'd be fun.
love it.
Yeah,
happy days. So you're a physics teacher.
that's right.
Before we actually get into it, would you like a drink?
Sure. What do we got going on?
So we've got a coconut gimlet, so gin based, banoffee pie old fashioned, which is rum and whiskey based,
Okay.
or a strawberries and cream milk punch, which is like gin and vodka based.
Hey, I'm curious about this milk punch business.
Okay.
Yeah.
A milk punch. Do you remember like strawberries and cream lollies
Of course.
growing up?
Yeah.
It should taste like that. It's what I normally describe it as. And it's quite good for a conversation like this because it's probably going to get heavy and this is a little lower ABV.
It's a little light. Hey.
Yes.
Cheers.
Cheers.
Yeah, it's nice. It's sweet, but it's a little bit more grown up.
Yeah. I mean, that's why I say it's like the lolly because it does have that sweeter.
Yeah, it's on the edge of cloying, but it's not quite there.
Yeah. Exactly. Anyway, alrighty. You're a physics teacher.
Yeah.
Thank you very much for coming on.
That's okay.
I am really curious as where this sort of love of physics comes from and what happens to steer you down the direction of not only one researching and learning physics, but then also wanting to teach it.
Yeah, okay. Well, I mean, I joke with my students sometimes that I forgot how much I didn't like physics at school.
Okay.
So I went through school. I loved maths. I enjoyed science. It's not that I didn't like physics, but I enjoyed the classical studies a lot, and history and that kind of thing. And then I got to university and I sort of forgot about that and took a degree in physics and ancient Greek.
Okay.
Yeah, so I learned some ancient Greek, some Latin, some classics, and then did maths and physics at the same time. And then got to the end of that and then realized that was a terrible career choice and that perhaps maybe I should have asked someone what a good idea would have been. Maybe engineering would have led to a job. I don't know.
It's really hard to teach ancient Greek, isn't it?
Yeah, there's not a lot of call for ancient Greek teachers. It's a fun hobby, but it's really enjoyable staying up late in a library with a number of different books doing translations. And then going off to a different library to solve physics and maths problems, and sort of getting out at 3 a.m. That was a good time at the time.
Yeah.
But there's not a lot of call for that as a skill in industry. So I got really good at taking exams, and it turns out no one pays you for that.
Yep.
Yeah. So I got to the end of that. I wasn't really sure what to do, but I had been tutoring for a long time, so that during my university career, I had lots of jobs tutoring different things. So I thought, I'll go into teaching. Really, it had that level of thought into it.
Okay.
I don't know if you're expecting a deep philosophical kind of rationale for that direction, but I didn't have that at the time.
Fair enough. Did you find that you're just you like teaching people things and that it seemed like a good fit?
Yeah, I like when people like learning.
Yes.
You get the feeling when someone's like, "Oh, I'm really interested in that.
Yeah,
I'd like to know more," and it's exciting.
Yeah.
So that's good. I so went to Teachers College. So that was fine, and then I ended up at a very weird school.
Okay.
So the school that I'm at is experimental to some degree.
Okay.
So I came to that school just a year after it opened. And so I was able to kind of build up the physics curriculum from scratch.
Mm-hmm.
And
that
then,
would have been fun.
And it was,
Yeah.
and now the way I do physics is very kind of project based. It's very different to the way, I was taught at school. We build trebuchets, and last year one of my students made an ion engine, and we did tests on that. And one of my students built a theremin,
Ah,
yeah, so
that's the little...
exactly, right? So she made one from scratch and
Wow.
never made anything before, but she's a musician, she plays with an orchestra. So that was like the hook in. One student made her own bass pedals and like investigated distortion.
Okay.
And distortion is a hard topic.
Okay.
It's
For what
very
reason?
theoretical. Oh, well, like, you can turn up distortion on an amp and go, yeah, that's more distortion, but how much though?
Yeah, okay. So it's hard to measure.
It's hard to measure. What it is if you have a waveform, the top and the bottom of that waveform can be clipped out.
Okay, yes.
And the amount of clipping is the amount of distortion. But how do you measure that amount of clipping? And how do you measure the effect on the waveform? So she had all these electronics plugged into an oscilloscope. And
What's an oscilloscope?
Oh, it measures wave.
Okay.
So imagine like some electricity with some waves. You
Yep.
plug it into the oscilloscope, it'll give you a little screen.
Okay.
With like what's the waves of the electricity
Yes.
at the moment.
Yep.
So you play guitar, electricity.
Yep.
Comes
It
out.
measures the frequencies, etc.
It's exactly it.
Yep.
It's exactly it. And so she was doing a Fourier transform on that to find out how much distortion there was.
Okay.
That's too hard. For a year 13, that's too much. But she loved it. And I gave her some credits, obviously. That was a hard way to earn those credits.
I can imagine.
Yeah.
That is quite, people spend their entire careers making bass pedals for distortion and things like that. So
exactly right.
Yeah, for a year 13 to just be like, this is my project for the year.
Yeah.
That is quite I could not imagine ever doing anything remotely close to that when I was in school.
So it's like through that and through that philosophy that I've learned a lot.
Okay. Yep.
Because you have to.
Yep.
Yeah.
So do you find that you get to do a lot of learning from the students as well?
Yeah. When there are projects that students want to do, I think it's really important that I have a good handle on what those are.
Yep.
So I've got a good sense for when a project is reasonable and when it's not reasonable.
Yeah.
But there will often be projects where I'm learning something.
Yep. So give me an example of a project that is not reasonable.
I've got two, one that won't be surprising and one that might be.
Okay.
One that's not surprising is I had a student once who in year 11 wanted to build a particle accelerator.
Okay.
So I was like, hey, it's year 11. It's not high stakes yet. Fine. Give it a go. We'll see what happens. And so he 3D printed a whole, like a big round thing, and we covered it in copper. It didn't really work, but, it was fun.
Yeah.
It was fun as an experience. Another thing is I've had students every single year asked to build a go-kart.
Okay.
And it seems really reasonable.
Yep.
It seems perfect, It's like, yeah, go-karts, but something about go-karts, they're cursed. I've never had a go-kart made.
Okay.
Not a single time have we pulled off a go-kart. So now when I just had a student the other day say, hey, could I build a go-kart? I'm like, oh, God. They're always so convinced.
Yeah.
So convincing. It seems so reasonable, but it never works out.
And, my first thought is like, why don't you make it smaller? Why don't you try and at least make like a motorized skateboard first?
Yeah. Well, I remember my first group of year 13s, I had a student who did that.
Yeah.
Spent a lot of time. He's a engineer PhD now. Spent a lot of time motorizing the skateboard. And that was really hard.
Yeah, I can imagine.
Yeah.
I can imagine.
Spent a lot of time on that. Pulled it off, broke it many times.
That's science.
Yeah. It was a good time.
Yeah, move fast and break things.
Yeah, that's right. That's right. But you need the type of person who can handle that.
Yeah.
Yeah, and also who isn't stressed out about all the English and chemistry work they have to do. They've got other classes.
Yeah, exactly. They would need to focus their attention on that skateboard.
Yeah, that's right.
It's gonna, a lot of trial and error, a lot of soldering.
A lot of fixing it when it breaks.
Yeah.
A lot of finding out why it's broken.
Exactly. That must be really challenging for, anyone that's into anything high-tech electronic. The fault finding.
Diagnosing. Yeah, it's tough.
I went through a stint as a audio engineer doing an apprenticeship, and my boss worked on a lot of big sound desks.
Mm.
And then when you have something that doesn't work on it and you're looking at this board and trying to find, one little transistor that has gone, or a solder
like
that's
looking at
broken.
the actual little pop capacitor,
Yeah.
just like anything.
I was just like, mate, this is a little bit out the gate difficult to sit there and comb through every little connection.
I'm sure, like, once you've done it for a little while, you go, oh, something broke. It's that fucking third capacitor on the left or something, You know what it is and you can go fix it.
Yeah, get a bit of familiarity with what you're working with.
Yeah, that's
but
right.
It just, for me, maybe I just didn't have the patience to sit down and comb through it all to try and figure it out. It was just, but I was very impressed when he did it.
Right, that's what I was. Isn't it great when people with like expertise, you just watch them do something that to you is
foreign concept?
Isn't that great?
Yeah,
I love it when I get to watch people really in their element, in their place of expertise, absolutely nail something. Yeah.
It is super, super, super interesting. Now, I was just thinking about, in terms of learning physics and also the classics. Did physics start with sort of the Greeks? Where did physics start?
Yeah, I mean, you could argue for a long time, physics and philosophy were very, very similar.
Okay.
So there were some ancient Greeks who didn't care very much about whether or not they were right from an empirical point of view. Like they'd have a thought and it's a cool thought, but it wouldn't occur to them, or it wouldn't be important to them to test that.
Okay.
And see if that actually works. So that's when we get Aristotle's elements. Everything's made of air, fire, earth, water.
Okay.
And there's some combination of those.
So they're the originals, the OGs.
Yeah, but there is a movement for empiricism, which is actually testing out ideas to see if they work. And there is a movement for like cataloging. How we'd go from a biology point of view, we'd kind of see what a species there might be and give them names, or we'd go and look at rocks and that kind of thing. There were people at the time doing that.
Okay.
And go and name every rock, which is a good instinct, This is still what we do. But when it comes to kind of why things are the way they are, there were lots of different ideas. So Epicurus was one of the first people to think of an atom, for example.
Okay.
But he did that by just thinking, hey, you get a long rod and you cut that in half, and then you cut that in half, and you cut that in half. There's got to be a point where you stop.
Yeah. When do you get to the smallest point where you can't cut it in half again?
You can't cut it in half anymore, right?
Yeah.
And it's called that an atom. Tomos means divisible. So you can cut it. So atomos is you can't cut it anymore. So it's the thing, ton atomon, the thing you can't cut anymore.
Okay. Interesting.
And so he thought of that, and that's good, but he didn't test it. And how would he?
Yeah.
Right? How could you possibly? They just didn't have the equipment to be able to do that sort of thing. So as time went on, we get to the point where kind of in medieval Middle East, in sort of Baghdad, you get a lot of trying to test ideas about astronomy by looking at the stars.
Okay.
And that's when we get to the point where we can go, okay, here's a big idea, and we can actually test it by looking up and seeing what happens, right? And famously, later on, Galileo with his telescope saw like the moons of Jupiter.
Okay.
We didn't realize other planets might have moons. And you go, well, if Jupiter has moons and they orbit Jupiter, how do we write that down? At the time, if you have Earth in the center of the solar system and you have all the other planets rotating around Earth and they kind of move back and forth, you can do it. It's a complicated system. Yep. Things called epicycles.
Yes.
First written down by Ptolemy.
Okay.
Ptolemy, one of the like the successors to Alexander the Great's empire, ruler in Egypt.
Okay.
Right. So Ptolemy first put down like this idea of epicycles, where planets sort of go one way. If you imagine the Earth, a planet goes one way and then kind of stops and turns around a bit and then keeps going. And it looks like it's doing that because we're orbiting the sun while they're orbiting the sun.
Yes.
And sometimes it looks like a planet can stop and then keep going. And so, if Earth is at the center, you can there's this complicated dance that planets are sort of going through from our point of view, and you can write it down And it's complicated, but it's doable.
Mm-hmm.
But then to have moons orbiting one of those things, that's too much.
Yeah.
That's
Yeah,
too
yeah,
hard,
yeah.
you know? So that's where the idea that if the sun is the center of the solar system is way easier.
Mm.
You can just, it's all circles. It's not a problem anymore.
Yeah.
You know?
So at this time in history, is this sort of when the division of philosophy and science happens?
I don't think so. I think at this point you still have a lot of polymaths. You still have a lot of people, like, we might call what they do physics in retrospect,
Mm-hmm.
but they also do mathematics. They're also doing medicine. They're also doing all sorts of things.
Okay.
And I think that's more because of a societal division. So we get some people who have the privilege, who are funded, you know, either by some kind of rich patron or often by the church to do research.
Mm-hmm.
You know, they're looked after by rich people.
Yep.
And so those people can often be doing all sorts of different things, you know, and slightly advanced fields in lots of different directions. The idea of a physicist who does physics is more of a modern invention.
Okay.
You know, and if you go to university at the time, there's no Bachelor of Science. You know, there's no Bachelor of anything. It's everyone does the same stuff. It's a course that you go there, you know, and there's some science, there's some mathematics, and there's some philosophy, and there's some theology, and everyone sort of does that.
Mm.
You know, so this idea of specialization is more of a modern idea.
Okay, and so that's because I mean, like in our physics, we know of, you know, you divert into quantum physics, and everything is now just getting kind of, you know, we've found the new atom. We're getting smaller and smaller again.
Yeah.
Type thing in terms of like, what about our information storage? What's the smallest thing we can store information on? What's the it's crazy how it seems like science is this never-ending organism that continues to replicate itself and get more and more specialized in certain areas. You know, you used to be, I guess, a doctor of medicine, and now you're a surgeon or a pediatrician or whatever, and it has all these specialist sort of avenues.
Yeah, because there's no way that as an oncologist you can keep up to date on every single cancer.
Yeah.
You know, so either you're a general oncologist, which is, you know, a general specialist, almost a contradiction in terms, or you focus on one very specific kind of cancer, and then that's enough for a whole career. Yeah.
And so in the world of like physics, there is a lot of mathematics.
Yeah.
And so when do you stop being a physicist and you become a mathematician and vice versa?
I like that idea. That's a good question, because there's a famous mathematician, I don't know, his name has just escaped me, I just read about him, who talks about how the deviation of mathematics from real world application from physics is like the beginning of the end for mathematics.
Okay.
You know, which is not true, but it's a fun perspective. Yeah. I would say, you know, physics uses maths, and so it's very applied. And so the type of mathematics that you use as a physicist is maths that's been proven to be useful.
Okay.
It does that. It describes motion, or it describes states of being. It describes like stuff, you know. As a mathematician, you're not so worried about it being real. You know, you're just saying, hey, what can we prove? Or what problems can we solve? And it sounds a little bit less useful, but there's quite a lot of that thinking that ends up being useful in surprising ways.
Okay.
It doesn't start off useful. That's not the motivation for it. There's a lot of, you know, we say sort of in mathematics, you start from a set of axioms, and then you're trying to prove things from those set of axioms. So you assume a couple of things, and then you try and prove some stuff.
Okay.
And then often the stuff that you're proving can just be ridiculous. For example, I think recently Google used AI, I don't think Gemini, to prove a couple of interesting theorems. And one of them is about the Kissing number of a sphere in higher dimensions.
Okay.
So what a Kissing number is imagine a sphere in 3D. How many spheres of equal size can you fit around it so they're just touching? Just kissing each other.
Yeah,
you know?
okay.
And you can imagine that in 3D, and imagine it in 2D. You get a circle. How many circles of the same size can you arrange so that they're just touching? And now, what about in 4 dimensions? It's not useful to think about 4 dimensions for a physicist, right?
I can't even imagine what a 4-dimensional circle would look like, let
Yeah,
alone
yeah,
a circle
yeah.
touching other circles.
Yeah, imagine something going that way, and then that way, and then that way, and then another one.
Yeah.
Yeah. Sometimes you can kind of visualize. So imagine you were flat. This is a classic thing about dimensions. I hope this is interesting. Imagine you're a flat kind of person in this plane.
Yes.
And you get a ball, and the ball rolls past your plane.
Yes.
You know, what are you going to see? You're going to see, to begin with, in midair, floating, defying gravity, this little circle. This little point, you know, and it's going to get bigger and bigger and bigger until it touches the ground, and it's going to get smaller and smaller and smaller again, and it's going to look
as
like
it moves past me.
Exactly.
Okay, so it starts small, gets bigger, and then
imagine the ball coming past, and you're just kind of scanning it.
Yeah.
You know,
You've
seen.
Because I'm seeing the start of the ball, and then it's getting bigger, and then I'm seeing the end of it. Okay.
Yeah. And imagine, you know, it looks like it's defying the laws of physics. It's floating in midair. You know, it looks ridiculous. And then imagine the ball instead kind of came this way and just kind of skirted your plane. You'd never see it touch the ground either. It would just kind of float and then disappear and then go away again.
Yeah.
And then also imagine you were in 3D, back in 3D, thank goodness.
Yeah.
And you were looking at a 2D person, you would see inside of them. To them, their skin on the outside is the outside of them, and you can't see inside. But from your perspective, you can look at their insides.
Okay.
In a way that's extremely foreign to them by just sort of coming out in a different dimension.
Yes. Right? Okay. Bizarre. Yeah, dimensions are hard thing to wrap your head around.
That's right. So applying that 4-dimensional sphere. Imagine a 4-dimensional sphere sort of rolls through our 3-dimensional like slice. Like this is a slice. We would see a ball in midair just get bigger, touch the ground, get smaller, disappear.
Okay. Yep. I wonder if that, because there is a lot of observation in physics, because I guess you have a theoretical space, which is all thinking about it, and then a practical space where you're testing those theories to see if they work and things like that. That depending on who the observer is and what their definition is of what they're seeing, like my first thought when we were talking about the 2D ball, it almost, I could see myself confusing that for motion. Starting small and then moving up and then getting small again, confusing that as motion as opposed to a different dimension.
Yeah, I see what you mean. But if you had the right kind, I guess, of equipment, you had the right frame of mind, you could probably tell the difference.
Yeah, okay.
If you knew what you're looking for. Yeah. So imagine we, from a physics point of view instead of maths point of view, we sort of pose a question: is there a fourth dimension? Are we only in 3 dimensions, and so we can only see it, but there secretly is a fourth dimension that we can't access? In that case, wouldn't we expect 4-dimensional objects to occasionally roll through our 3-dimensional slice? And we'd see things sometimes where things pop into existence and then out again. And, we can look for that. We don't see it. So it doesn't rule out the fact that there is a fourth dimension, right? It doesn't disprove it, but it's not strong evidence, So probably it's not there.
Yeah.
So we go beyond thinking about what would it look like to, okay, well, do we see that?
Yeah.
A classic example as well is white holes. Have you heard about white holes?
I haven't heard of a white hole.
Have you heard of a black hole?
I've heard of black hole.
So black holes were first predicted by Einstein from what are called Einstein's field equations.
Okay.
So Einstein's field equations are a bunch of kind of requirements that us space-time needs to follow. And then we look and we see, okay, there are a bunch of different possible space-times. Does that match what we live in? One of the things the equation predicts is black holes, that there are points of infinite density.
Okay.
Right? And it also predicts the opposite, white holes.
Okay.
And when he predicted them, there was no evidence for it. So there's no way to know that the maths is right. It's not like we look at that maths, go, oh, it predicts these things with black holes, and just believe it.
Yeah.
We need evidence.
Yeah, we need to be able to observe it.
You got to observe it. You need data, right? And so I think in the 70s, the first experiment was run about this. Maybe the 80s leading into the 90s, very long-term experiment, where we just pointed a telescope at the middle of the Milky Way galaxy just to see what happens. And then when we did that, we found a lot of very, very large, very, very bright stars, all moving very, very quickly in the center of the galaxy,
Okay.
rapidly orbiting the same point where nothing was.
Okay. Yes.
And
Yeah.
we're like, okay, well, nothing's that we can't see anything because it's black.
Yeah.
You know, but we can, from the orbit of those stars, calculate exactly what the mass is. Like, not exactly, but like pretty close what the mass is. Evidence for a black hole.
Mm-hmm.
Evidence there. But we look and we look and we look, no evidence for a white hole. You know, so the maths is saying, hey, it might be this white hole thing. Very, very good maths. A lot of different observational data supports this mathematical framework, but we don't see a white hole. There's no white hole.
Mm.
You know?
And does that kind of drop into the theory of, now this is, where my ignorance is, I don't know if it's a theory or it has 100% been proven, but that every action has an equal and opposite reaction. If you have a black hole, you must have a white hole because that's the equal and opposite reaction.
Yeah, I mean, I guess, when it say reaction, we mean force.
Okay.
So that means like a specific thing that's got a definition. And so you kind of want to, in what you say, kind of extrapolate that to more of like a philosophical generalized framework, right?
Mhm.
And I guess it's satisfying. It feels good,
Yeah.
doesn't it?
Yeah,
And so
it seems to make sense.
it kind of works,
Yeah.
a little bit of yin yang,
Yeah,
right?
yeah.
Like a little bit of balance.
Yeah.
It feels kind of right. And yeah, you got to be careful.
Okay,
You gotta be
so
careful.
that's something that trips people up.
Yeah. If you get too worried about how pretty the maths is, and we talk about beauty in mathematics,
Okay.
without thinking about, is that actually real? Can I get evidence for it? And is there evidence for it? Yeah, it's an easy trap.
Okay, yeah,
You know?
I've trapped myself already.
Yeah. I mean, because it feels like it should work, but then
Yeah.
if it works, we don't see it.
Interesting.
So I guess not.
I mean, is there a possibility that we confuse a white hole for a star? Because, I mean, when we are observing it with a telescope or something like that, we're essentially just seeing light. Wouldn't a white hole be putting off light? Like a star?
Well, what we do, we're not just looking at light, we're looking at the very specific type of light.
Okay.
So we're able to, different stars will emit different kinds of light. So from the light that we're seeing, we're able to sort of get an idea of what this star is, what's going on inside of it, what it looks like.
Okay.
And there are very specific sort of light profiles. Partly it has light because of it's hot. Anything that's hot emits light.
Okay.
We're emitting light right now. We have heat. We're emitting light. Do you know what light we're emitting? There's a little test. You didn't know there was going to be a test.
No, I didn't know there was going to be a test.
Guess what light we're
I
emitting.
want to say like an infrared.
You're exactly right.
Oh, bingo.
You're exactly right. And so obviously our eyes can't see infrared.
Yes.
But you get like a little heat camera or something, and you can see the light that we're emitting.
Okay. Yeah. Yeah.
Brace yourselves. It's sponsorship time. I know ads can feel like the Broccoli of podcasts, but today we're talking about the Bar Society, a company I own and operate. So think of it as supporting my broccoli farm. This goes out to all cocktail lovers and hospitality pros. Are you ready to elevate your drinking experience? Introducing the Bar Society, New Zealand's leading clear ice supplier. Whether you're stirring down a classic old-fashioned or crafting the perfect gin and tonic, there's no substitute for crystal clear ice. Not only does our ice look stunning, but it also melts slower, keeping your drinks colder and your flavors perfectly balanced. From home bartenders to high-end establishments, the Bar Society's here to bring your beverages to the next level. Order today and see why we're trusted by the best bars and restaurants in New Zealand. Visit thebarsociety.co.nz and let us transform your drinks. The Bar Society. Elevate your drinking experience.
Yeah. So anything that has literally more than zero energy is emitting some kind of light.
And light is essentially the purest form of energy.
Yeah. I mean, there's other types of energy. Certainly light is how electromagnetic energy gets from one place to another. So you can think about things in that way. But energy is much more of an abstract concept. You can't sort of point at an object like a photon, which is a particle of light, and say, that's energy.
Yeah,
It has energy. It carries energy. Is it energy? No, it's just a more abstract concept we use to describe
Okay.
sort of situations, right? From the size, I was saying, stars emit light because they're hot.
Yes.
This is called black body radiation. And then the type of light that we see is going to tell us how hot the star is.
Mhm.
And then from how hot the star is, we can find out how big it is.
Okay.
Because if it's hotter, it's bigger.
Okay.
The heat is coming from nuclear fusion in the core. And if it is big, it can do more nuclear fusion in the core.
Okay.
And so it can do more heat.
And what allows that to happen is just the fact that there's more mass and more pressure pushing into the center?
Yeah. It's
Okay.
just squeezing it real tight. Yeah.
And so the more mass you have, the more pressure you can exert on the center, and then the more energy the nuclear fusion would produce and put off.
Yeah, more nuclear fusion and bigger nuclear fusion.
Okay.
Like our sun is not big enough to, at the moment, to take helium, which is the product of the hydrogen fusion that it can do. So at the moment, hydrogen fusion, all good for our sun, totally fine. Hydrogen's the smallest element. Smash some of those together, slightly more complicated process, but you get helium.
Okay.
It's not big enough at the moment to take helium, smash it together.
Okay. So it can bond hydrogen with hydrogen, but it can't bond helium with helium.
Yeah.
And when you have bonded hydrogen with hydrogen, you produce helium. That's essentially the byproduct.
Yeah. That's right. And there's details, there's steps on the way, but yes.
Yeah.
And then by doing that, you get out energy.
Okay.
Right? Energy is released from that process.
Yes.
But some stars are big enough to squeeze helium together, and you can get other products from that. And that's where we come from.
Okay.
If you've ever wondered, where does all this stuff come from?
Yeah.
All these elements, I don't know, copper, metal, the silicon in glass.
Yeah.
The carbon in wood, where does all that come from?
Yeah.
It comes from nuclear fusion in stars.
Okay. And so the more massive the star is, the more nuclear fusion that's happening. Is hydrogen lighter than helium?
Yeah. Hydrogen is just a proton. It's just one thing.
Yeah. And so then helium is slightly heavier than hydrogen.
Yeah.
And requires more energy to fuse it together.
Yeah.
And then what produces glass is essentially something even bigger again that can bond whatever it needs to be able to make silicon and other denser things. So I think about that in terms of I might be wrong in this, but Earth has an iron core.
Yeah, iron, cobalt, and nickel. Yeah.
Iron, cobalt, and nickel, molten.
Yeah, I think mostly iron.
So is there nuclear fusion happening within the center of the Earth that has been able to bond things together to be able to produce the iron? Nickel?
No. So the iron, we didn't make the iron. We being the Earth. Earth didn't make that iron.
Okay.
That iron was out in space.
Okay. So a star made that iron?
A star made that iron.
Okay.
Exactly right. And iron in particular is the end for stars.
Okay.
Iron is the death knell for stars.
Okay.
So you can keep getting energy out. If you think of a periodic table, you get those elements, smash them together. You can keep getting energy out until you get to iron.
Okay.
Iron is the most stable nucleus. It's the most stable element. You fuse two iron nuclei together, you're not getting energy out like how a star.
You've just got a bigger iron.
It requires energy. No, you'll get higher things than iron.
Okay.
For example, gold, silver, mercury, lead.
Those
are all those are all heavier than iron.
Yes.
But a star can't make those things and give out light and energy and heat because of it. Those things require light and energy and heat. They kind of suck it up. So you have this sort of curve where, to begin with, fusing hydrogen together gives you heaps of energy. And then as you go up higher in the periodic table, you get diminishing returns. And then it comes to a point where you get to iron, you're done. You're not getting energy out of that. So where do all the bigger things come from is a good question.
Yeah.
Imagine when a star, a really big one, gets big enough that it gets to an iron core. The fusion stops. The thing is that a star is kind of this plasma, it's this gas. It's not dense, it's not like rock.
Okay.
So that gas is trying to pull in on itself. all the gravity of all that stuff that a star is made out of is trying to collapse the star in.
Mm-hmm.
But it can't do it because all the fusion in the core is exploding it back out again.
Okay.
Right? And so a star reaches this equilibrium where the gravity is trying to pull it in, but the fusion is exploding it back out, and it kind of has this stable sort of size.
Yeah.
Right?
Yeah.
When the fusion stops, it starts all collapsing in.
Okay.
And then it bounces, right, and explodes.
Yep.
And during that bounce and the explosion, which is called a nova, there's heaps of energy just kind of around,
Yeah.
for free.
Yeah. Yeah.
And that is when all the heavier elements like gold, like uranium, for example, like really heavy things, that's where all that is made.
Okay, so as the star collapses into itself, it exerts so much pressure and energy that it can then fuse.
There's plenty to go around.
It can fuse heavier things together, and you produce things like gold.
Yeah.
Okay, interesting.
Yeah.
And so then, on its way out, you're obviously not left with a gold core. You're throwing gold out into the solar system.
Yeah, or what's left of it. Because,
Okay.
the star in the middle exploded.
Yeah.
Mm.
Okay, interesting. And so, I'm like...
Yeah, so imagine, okay, I know, I don't think we've yet completed a topic, but it's okay. I quite like talking about this, so we'll do it.
This is so interesting.
Yeah, so the Big Bang happens.
Yes.
And from that, mostly hydrogen, helium, and lithium, the first three elements in the periodic table, are made.
Yeah.
Everything that's heavier doesn't exist yet.
Yes, okay.
And all that hydrogen, mostly hydrogen, can come together due to gravity. And it's sort of spinning on itself, and it can form galaxies. And those hydrogen the hydrogen kind of makes little clusters. And those little clusters can collapse together to form stars. And then the stars can be really, really big, really hot, burn through their hydrogen, forming a lot of helium, burn through the helium, forming heavier elements, but they're not long for the world, or the universe, I suppose. Big stars burn hot and live short lives.
Okay.
They burn hot, they die quick.
Yeah.
Collapses in, explodes. But just because it explodes doesn't mean all the stuff is gone. It's just spread out now.
Yeah.
And it was huge. So there's lots of stuff. Some of that stuff can kind of come back together after a little bit of time. New star.
Yeah.
But this star's a little bit more interesting because there was lots of stuff the first star made. And so this star can maybe do a little bit of different fusion. And maybe there's like bits of rock around as well. And maybe those bits of rock can sort of start to form planets and whatnot.
So what has bonded together to make rock?
The rock is just like things like silicon and carbon and a bunch of different kind of elements. Right?
And that is a byproduct of what the star did the first time.
Exactly.
Okay.
Right? So we go from a big, huge, kind of bright, hot star, but with nothing interesting in it, mostly just hydrogen. It explodes, and then as it explodes, kind of more interesting stuff is made. And now a new star can be born that's a little bit more interesting. It's got more stuff around. And then eventually it will explode, and even more interesting stuff. Gold, uranium, big, heavy stuff, lead, big, heavy stuff can be formed. And then that can all come together again. And that's our sun. Our sun is a third generation star.
Okay.
And so all of the stuff, our sun is hydrogen. It's like 99.9% hydrogen, I think. That's all in the center of the solar system because it's light. It kind of moved in. All the heavy stuff kind of like hung around the outside.
Okay.
Right? And eventually formed our planets. And so the Earth has all this stuff on it.
That all came from the death of stars.
Yeah, I think about that sometimes. We've got this whole periodic table. There's like one or two elements on that periodic table we don't have.
Okay.
Everything else we have.
Yep.
I just think that's crazy.
That is crazy.
Right? Just in like mines.
Yeah.
You just dig it up and you get yttrium, whatever yttrium is.
Yeah, never heard of it.
Yeah, it's one of the elements.
Okay.
Or I don't know. Yeah, gold's weird.
Well, gold's an interesting thing, and when I think of something like gravity, I think gold is obviously heavy.
Yeah.
When it's floating out in the nothing of space, is that the thing that exerts more gravitational force on lighter particles like helium and hydrogen?
Yeah.
And so, does the heaviest element that dying star put off then become the core of the next star that comes in, type thing, because it has the gravitational force to drag things into it?
Yeah, I mean,
and slowly cluster.
I think that's a good question. I'm not sure, but no. Normally, the core of the star is hydrogen.
Always hydrogen because it's lighter and it can actually be pulled through.
Yeah, that's right. You know how satellites in orbit stay up there,
Yes.
you know?
Yep.
And the way they stay up there isn't by going up, it's by going sideways really, really fast.
Okay.
Right? So all the things in orbit, like the International Space Station, that kind of thing, are being pulled by the Earth's gravity downwards.
Yes. Okay.
Right? But like gravity's still there. Sometimes people think you get to space and gravity turns off, but
Yeah.
it doesn't.
Yeah.
It's just that they're going sideways really, really fast. So they're falling, but also going sideways. And so as they go sideways, when they go to fall, the Earth is curved away. Right? So imagine throwing a rock so quickly that the Earth's curve matters, and the rock kind of like goes even further because
Just continuously falls
it's
and never
continuously
touches
falls.
the ground.
And never touches the ground, right? So they're going sideways really, 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 really fast. And that's what keeps them up there.
Okay.
Similarly, when a star explodes, all the stuff was spinning. It had angular momentum. It was all rotating around. So it doesn't necessarily all spiral in. It can be around in stable orbits, just like the Earth doesn't necessarily spiral into the sun. You know, we're in a nice stable orbit. So all that heavy stuff could be hanging around the outside.
Yep.
And instead what happens is you've got a big heavy core like gold or like iron, cobalt, and nickel. You know, it will start to suck up everything near it.
Yes.
And so that can form the core of something. There's not enough gold to really form,
Yeah.
you know, there's barely any gold. Heaps of iron.
Yes.
You know, plenty of that around. It's heavy enough, you know. So it's sort of sucking everything else up, and there's not much like dust left. And that's the birth of a planet.
Okay.
Yeah.
Yep.
You get.
And so what is it essentially the core nuclear fusion which differentiates a star from a planet?
Yeah.
Okay.
You know, so sometimes you'll hear Jupiter be called a failed star.
Okay, I've never heard that.
Yeah, sometimes Jupiter gets called a failed star, which is a sad thing to say to someone.
And because it's a gas giant, isn't it?
Mm.
And so, as you said before, stars are mostly gas.
Yeah.
That is why it's referred to as a failed star, because it could have become a star because there was so much gas there.
If it was bigger. Yeah,
okay.
it would have been. And so you can imagine all the gas in the center of the solar system might have like come together and formed a star. And any gas left over far away might have formed its own star.
Yes.
And so that does happen. We look at solar systems nearby, and sometimes there are multiple stars in that solar system that have formed.
Okay.
You know, sometimes a star might be captured or something. So like two stars kind of wandering next to each other might sort of capture together. But sometimes two stars might be made from the same stuff.
Mm-hmm. Okay. Yeah. And I guess, you know, when two planets are captured in the same sort of orbit, they would form together to make one bigger planet.
Yeah, eventually.
Essentially.
Yeah.
And so does that happen with stars also? They form together and make a bigger star.
Yeah. Stars can merge. Absolutely. It's probably not that you get two stars and then they merge together to form a nice big star. It's more that because the tidal forces involved, the gravitational forces are immense.
Yeah.
So it's more like when two stars get next to each other, they blow each other up.
Yeah.
Tear each other apart and kind of form like a big mass of all sorts of stuff, which might then come together to make a new star eventually.
Okay, but could potentially form two new stars.
Yeah, maybe. Yeah.
Yeah. Okay. So the possibilities are kind of endless.
Yeah.
It could even blow each other so far apart that you have three new stars form that are slightly smaller.
Yeah, maybe.
Okay.
Yeah.
Interesting. Because isn't that how sort of our moon formed? It's believed that a planet crashed into Earth. There's a bit of a debris field. Our moon formed, and the rest of it collected around our Earth, and that's how we ended up with a moon.
Yeah, you're exactly right. And that came from going to the moon.
Okay.
Digging up some moon stuff, bringing it back, and going, "Hey, this is just the same as our stuff. This is just Earth stuff.
Okay.
It's very, very similar." And that's suspicious. You know, so how did all that get up there? You know, why is it a very similar kind of mineral composition? Well, a good theory is we got hit by something big. It's given the name Thera.
Right? Thera, okay.
Yeah, and then that caused a whole bunch of, you know, gloopy stuff.
Yep.
You know, and that gloopy stuff eventually became...
And I imagine that happened very early on in the piece. And
yeah.
We were still kind of molten.
Yeah, exactly.
And forming, and so, yeah, it's not exactly like it's hitting
no
a
atmosphere.
Rock. Yeah,
no, we didn't have like clouds and rain at the time.
Yeah.
This is pre rain,
yeah.
right?
This
It's
is
pretty early.
pre-person.
Yeah. Oh, yeah.
We're going back
There's
a few haircuts.
There's no life yet.
yeah. Okay.
Yeah.
Interesting. So then, what stops a moon? Like, we're talking about Jupiter's moons first being observed.
Yeah.
And I'm thinking, like, do stars have moons because Jupiter is looked at as a failed star and that has moons?
Yeah.
And so had those moons formed in the same way that our moon has formed?
Probably not. I
Are
would
they
say
just
that
more like asteroids that got
Yeah.
caught in the gravitational?
could be, or just like stuff that's left around and that kind of thing. But I mean, you raise a good point in that it's hard to tell. The way we found out about the moon is by going and digging up some moon stuff, and we haven't gone to any other moons and dug up moon stuff from them yet.
Yep.
So maybe one day we'll have a really clear idea of exactly where all the different moons came from. But I would be surprised if they're all there, because there's a lot of them. If they're all there because an asteroid hit a planet and then stuff came out, I think it's more likely that they were caught.
Okay.
And captured. Some of the moons of Jupiter are very, very big, bigger than Pluto, for example. That if they were, kind of in an orbit, we might have almost called them a planet in their own right. But they're orbiting Jupiter, so too bad, they're moons.
And so this, like, kind of loosely, a moon is defined by what it orbits, as opposed to what it formed.
Yeah,
of.
I mean, we made up the word.
Yeah.
We made up the word moon. We made up the word planet. They're not following our rules.
Stay in line. Stay in your lane. You're a moon.
Yeah, exactly. So there was all that controversy when Pluto was demoted from being a planet. Remember?
Relegated.
But it's just a name.
Yes.
We decided what the name is. We can call things whatever we want, but it doesn't change anything.
Yeah.
Right?
Yep.
So moon goes around a planet. Planet goes around the sun. Is there a significant difference between a moon going around a planet and a planet going around the sun? Not really.
Yeah, planet's kind of like a star moon.
Yeah, you want to call planets moons? Totally fine.
Yeah.
Totally fine.
Yeah.
Planets have that name planets because when you look up at the night sky, a clear night sky, not like in Auckland, you can see them moving around.
Okay. Yeah.
Like stars still, planets move.
Okay.
It's sort of on that background. So that's like the historical context of it.
So what do stars then orbit? They obviously orbit within a galaxy, and I'm guessing the center of the galaxy is something like a black hole, because everything is orbiting it. So stars are all orbiting black holes.
Yeah.
Planets are orbiting stars. Moons are orbiting planets.
Yeah.
Where do asteroids then fall into it?
They're just bits and pieces.
And are they orbiting anything?
Could be. So Halley's Comet, for example, is orbiting the sun, just on a really, really strange orbit.
Okay.
Really unstable. Well, maybe stable. Maybe unstable is the wrong word, but very elliptical.
Okay.
Not like a planet. There's an asteroid belt between Mars and Jupiter.
Mm-hmm.
All those asteroids are orbiting the sun.
Yes. Okay.
Yeah.
So, okay, that's something I haven't thought of. Could you maybe think of the asteroid belt as the beginning of the formation of a planet, that eventually those thousands of rocks are going to turn into one rock?
Yeah, and
because they're going to crash into each other.
Yeah, and there are sort of small planets in there.
Okay.
Ceres, for example, is round. So pretty close to being a planet.
Mm-hmm.
It's rounded rather than sort of irregular, and it is in the asteroid belt.
Okay.
I can't remember how big it is compared to Pluto, but I think it's a very similar size.
Okay.
So if Pluto's a planet, Ceres is a planet, I don't have a problem with that, because they're just words. But so there are some things in there. I think the reason why the asteroids in the asteroid belt haven't formed planets already is because of the influence of Jupiter.
Okay.
So Jupiter has quite a large gravitational pull, and it can disrupt stuff around it. And I think it's disrupted the asteroids from really coming together. And the asteroids kind of form, in the asteroid belt, three main clusters because of the gravitational influence of Jupiter. So I think it's stopping it coming all together.
Okay.
Yeah.
Interesting.
Yeah, we're quite lucky with that, because Jupiter's gravitational influence also stops errant asteroids from just around the place from reaching us.
Okay, so it's a bit of a protector with its gravitational force, and it helps throw things
Yeah,
of course, when we start aligning with it, that could potentially hit us.
yeah, we're quite lucky,
Mm,
especially since, we talked before about how planets will form from exploding dust and that kind of thing.
yes.
If that happens, all the stuff is in the middle.
Yeah.
So
Yeah.
if you've got a big planet like Jupiter, do you expect it to form far away?
Yeah.
Or do you expect it to form quite close to a
Yeah,
sun? You
yeah.
expect it to form quite close.
Yeah.
And so when we look at other solar systems and we see planets in those solar systems, there are big Jupiter-sized planets really close to the sun, like where Venus or Mercury
Mhm.
is. But in our solar system, we got kind of little rocks, Mercury, Venus, Earth, Mars, before
Mhm.
you get to the big things.
Yeah.
Right?
Yeah.
So we're quite lucky. So there's a theory, I think, that Jupiter formed close to the sun and was kicked out from some reason. Maybe something hit it, some kind of gravitational something happened,
Mhm.
and it moved further out. And that's very lucky for us because then it can protect us from asteroids. And that
Yeah.
kind of
Yeah.
thing.
Yeah. From the outside.
Yeah.
Interesting. So, when it comes to gravity and orbit, what is the more important factor? Is it the mass or the size?
The mass.
The mass.
Yeah,
And
how
so
much stuff
your
there is.
mass
Yeah.
is how essentially heavy it is.
Yeah.
Okay.
Yeah. How much
Because
stuff is there? Yeah.
yeah. So Jupiter is so big, but it's mostly gas.
Mm.
And just naturally, I think gas is lighter than a
Yeah.
solid.
Yeah. Yeah.
And
There's a lot of it though.
yeah, it's so much bigger that it still
Yeah.
probably weighs more than Earth.
Way more.
Yeah,
Way
yeah, yeah.
more. Yeah.
And is it just that the fact that the sun is so big that its falling motion, its orbit, is really the tightest circle that it could be? Or it could be tighter and spinning much faster?
It could be tighter.
Okay.
Yeah, but it's not good.
Yeah.
That's good that that's the case. Yeah.
Yeah. Okay. Thinking about energy and planets or asteroids, any kind of massive object hitting each other, when you have that force and the explosion and material gets thrown out anywhere, that's energy being pushed out somewhere, obviously.
Yeah.
So when it comes to like our planet and the moon, does the moon also have like a molten core or a heavy core like we do? Because it seems essentially dead because it's tidal locked as well, right? So
yeah, it's tidally locked. Yeah. I don't think tidally locked would make it dead.
Okay.
I think it has a hot core, but I don't think
Okay.
it's molten. It certainly has an iron core.
Okay.
We can tell this, like, we do gravity mapping. So we look at the very specific gravitational changes from one point of the moon to the other. And from that, we can guess about what's inside. It's tough. The way we know about what's inside the Earth is because we've got this really handy tool that allows us to see what's going on inside, called an earthquake.
Okay.
We look at earthquakes, and then earthquakes allow us to kind of piece together what's going on inside of the Earth, and it sort of tells us that there's these layers and that kind of thing, because we can see earthquake waves bouncing off these layers. Right? Really handy. We don't have that on the moon, so we've got to like find other ways of seeing what's inside.
And so we don't know if there's moonquakes.
I think there are moonquakes. I think that's the thing.
Okay.
I think that's the thing, but I think they come about, like our earthquakes come about because of our plates,
The tectonic plates.
The tectonic
grinding.
plates, thank you. It went straight out of my head. We've got tectonic plates floating on this kind of moving sea of molten rock, right? The moon doesn't have that.
Yes. Okay.
So the moonquakes come about because of tidal forces from the Earth. You know how the moon exerts, causes tides.
Yep.
We cause tides from the moon. There's no water there, but there is a rock, and so it kind of squeezing the moon a little bit.
Okay.
Which causes some moonquakes, yeah.
Okay. Interesting.
I don't know how useful those are for inside the moon, though. Yeah, I don't know how much we know about what's inside the moon.
Yeah. And is there any way that like we have sensors that detect earthquakes? Could we perhaps send sensors to just land them on the moon? And be like, fucking measure the quake.
There's heaps of stuff on the moon.
Oh, okay. There is heaps of shit
we've loaded that up.
Yeah.
We send stuff there, not all the time, but there's plenty of stuff up there.
Yeah.
I mean, send satellites to like orbit the moon and take a look at things. Yeah, all sorts.
I've never really thought too much about the formation of the things and what makes them all what they are.
Yeah, I don't. I mean, that's neat. It's a neat kind of narrative.
Yeah.
But then I also think it's so strange. If you go to, if you go to Mars, there isn't so much stuff there.
Mm.
We've got heaps of stuff. I'm just thinking the periodic table.
Yeah. Have we
Yeah.
sent stuff from Mars back to Earth?
Yeah,
Yeah.
pick up little bits of rock and that. kind of
Okay,
thing. Yeah.
yeah.
I mean, but the most recent rovers have little labs
Okay.
on
yes.
site, so they
Yeah.
will dig up some rock and then do a little bit of analysis and send back the data.
And are they finding similar things to what we have on Earth?
Yeah, slightly different,
Okay.
you know, but like not nothing very unexpected. I don't think. I think we mostly are able to guess pretty well what Mars is made out of, and we're looking for things that might surprise us.
Okay.
Things like water.
Yes.
If we find water, that'd be great.
It has ice, right?
Yeah, some
Like
ice.
polar caps.
Yeah.
So that is a clear indication that there's water
Yeah.
there? Like,
Yeah,
is
yeah.
all ice water?
Yeah. I mean, you know, I guess you could have other kinds of ice. We talk about oxygen ice, and like you can have carbon dioxide ice, dry
Okay.
ice. But
Yeah.
we're talking about water ice here.
Yeah.
We definitely mean water ice. And yeah, there definitely is some there. And then also we're looking for where is there water where we don't expect to find it.
Like in an aquifer or something like that.
Yeah, essentially we're trying, you know, we've got this idea and we're trying our best to prove ourselves wrong.
Okay.
Because if we prove ourselves wrong, we get really interesting results from that, right?
Mm.
So we're not looking for water where we already expect to find it.
Yeah. We're looking for a beach. Can
Yeah.
you spot the beach?
Yeah,
Yeah.
a waste of time and money that would be.
Yeah.
It's like we thought we'd find water and we did. We've learned nothing.
Yeah.
Right?
And so how are we searching for it? Are we like drilling?
Mhm.
See if anything bubbles up, see what's liquid under
More
the
like
surface.
drill a little core
Okay.
and then bring it and bombard it with lasers
Mhm.
and whatnot and see what comes out.
And we just kind of
Yeah.
check for if there's like, you know, the H2O molecule or something hidden in there.
Yeah, I mean, what we're doing very specifically is we're looking for the hydroxide bond. So
Okay.
the bond between the hydrogen and the oxygen is a very characteristic bond. You just sort of shine some infrared light on it, and the hydroxide bond soaks up that infrared light.
Okay.
It's really reactive to it. So you can imagine if you have a detector, some water, and a source of infrared light, shine the infrared light on it, and then you're not going to get the stuff that the water sucked up.
Yes. Okay.
Yeah.
Yeah.
So we're looking for different stuff is going to suck up different bits and pieces from that light. And so we shine some light on it, see what comes through, and then that gives us a good indication of what's inside.
Okay.
Yeah, or what it is. It's called spectroscopy.
Interesting. So now I'm thinking like scaling out my view of the solar system.
Yeah.
So moons are orbiting planets, asteroids are kind of orbiting whatever they decide to orbit. Planets are orbiting suns.
Yeah.
Suns are orbiting a black hole.
Yeah.
Are black holes moving and orbiting something as well? Are they orbiting an even larger, maybe a white hole?
Hey, it's a good thought. Yeah. But the black galaxies themselves aren't necessarily orbiting like a larger central core, but there is structure there.
Yes.
So when we look at galaxies, and you know, there are people whose whole thing is they look at telescopes, find out where galaxies are, map them.
Yeah.
We find some very suspicious sort of lines where there's more galaxies here, and there's sort of no galaxies in between, and then more galaxies here. So it's less that there is kind of this rotational kind of shape, you know, that doesn't scale up, but there is structure. There's kind of like tendrils where galaxies tend to accumulate, and they're accumulating there because of gravity.
Okay. And that gravity is being exerted by a black hole?
Yeah, all the stuff, all the mass, you know? It's not as strong at that distance, but it's enough.
Here we go again. It's ad time. But don't hit that skip button just yet. Today's sponsor is First Class Cocktails, another company that I own and operate. So technically it's less of an ad and more of me shamelessly promoting myself. You know what's better than a great cocktail? A great cocktail with no effort. Meet First Class Cocktails, New Zealand's premier provider of premium bottled, ready-to-drink cocktails. We're talking about perfectly balanced flavors, made with the finest ingredients, and all you have to do is pour, sip, and enjoy. From timeless classics like the martini and the old-fashioned, to bold new creations like our pineapple and chili margarita, First Class Cocktails ensures every drink feels like a first-class experience. Whether it's a night in or a party out with friends, we've got your cocktail game covered. Order now at firstclasscocktails.com and raise your glass to effortless luxury. First Class Cocktails, because every moment deserves to feel first class.
And so eventually, in terms of the end of the galaxy, everything's going to get swallowed up by the black hole?
Yeah, I
If
mean,
we zoom way out?
I think, the black hole, just because it's a black hole doesn't mean it has any kind of extra sucking power.
Mm-hmm.
It's just heavy.
Yeah.
So we're just orbiting it because it's heavy. And just like the Earth has a stable orbit around the sun, we have a stable orbit around the black hole. So it's not necessarily inevitably sucking us all
So
up.
we're not getting closer or further away from it. We're just nice and stable, the same way a satellite is around us.
Exactly like that.
Okay.
Exactly like that, right? So eventually things will die,
Yes.
but not because they're all going to be sucked up by black holes, although I suppose black holes will sort of absorb the very last of anything that exists, right? We're talking, I think it was 10 to the 90 years, which is a long time.
Yeah.
It's a one with 90 zeros after it.
Okay, 10 to the 90 years.
Yeah.
Yeah.
That actually recently, that number got revised down.
Oh, okay.
Yeah, we thought it was a lot longer, and then we realized, well, it's a little bit shorter.
Mm.
Paper came out just recently. I think it was 10 to the 90. Yeah.
And so I guess people are constantly working on mathematical equations to figure out how long the planet is going to survive for and how long the sun's going to survive for, and macro scale that out to the universe and things like this.
Yeah, I mean, it's a pretty easy problem.
Yeah, okay.
So it's
and it's not really one that we're gonna. It's it's not happening tomorrow.
Yeah, the sun will eventually run out of fusible hydrogen.
Yeah.
At that point, it will expand.
Yeah.
And it will destroy the Earth.
Okay.
Whoops.
Yeah. And that is not due to anything gravitational. It's just the fact that the sun is now expanding.
Yeah. It'll get big.
Yeah. And so the amount of nuclear fusion that is happening in the core is now overpowering the gravitational force of pulling it in, that the nuclear fusion pushes it out.
It will bounce.
Okay.
It'll do that bouncing thing. Yeah.
But it would stop at a point.
It would stop at a point and it would start to fuse helium in the core and it will kind of come back down again.
Okay.
But we can map that process pretty clearly.
Mm-hmm.
It's complicated. It's not simple. And the details, are a little bit interesting.
Mm-hmm.
But it'll wipe out the Earth at that point. It's a long way away.
Yeah.
It's not something worth worrying about.
Yeah, okay. I'll cross that off the list to get my doomsday.
Don't book it on your calendar.
Yeah.
Right?
Oh man, this is so interesting. I'm learning so much from you. Thank you very much.
That's okay.
So
I'm glad we're talking about space stuff.
Yeah.
That's quite fun. It could have been anything, but space is good.
Space is very interesting, and I kind of wanted to get an understanding of where some of the fundamental knowledge that we have about space and the ideas sort of started from. And this is where I was kind of curious about the division of maths and sciences and things like this. Because like Einstein, was he a physicist or was he a mathematician?
He was a physicist, but he had great advances in mathematics.
Okay.
It's just the reason why he's interested in maths is because you can use it for physics.
Yeah, okay.
The line is blurred there. It's not like as a physicist you go, I'm not going to do that. That's maths.
Yeah.
You do it if it's useful to solve the problem.
Yeah.
That's how maths that we don't expect to be useful becomes useful.
Mm-hmm.
When someone who wants to use it for something goes, oh, actually, that'll really work with the problem I'm working on at the moment. Great.
Yeah.
They use it for something. Right?
Yeah, okay. Because my partner and I recently watched the Oppenheimer movie.
Oh, yeah. Yeah.
And sort of, one of the big concerns that Oppenheimer had talking to Einstein from what was depicted in the movie was the fact that if they do create nuclear fusion, was it fusion or fission?
Fusion.
No,
fission.
Fission.
Sorry,
so that's the
right.
splitting.
Yeah.
Right? Fusion is the joining, and that's what the sun does.
Yeah.
And then fission is the trying to cut the atom.
Yeah. Do you remember
again.
how I said like iron was the endpoint of a star?
Yes.
And then when things get bigger than iron, you don't get energy out of bringing them together, but you do get energy out of taking them apart.
Okay.
Right? So there's the iron is like the cutoff point between energy from fusion or energy from fission.
Okay.
Yeah.
And so when it comes to a nuclear bomb, we're doing fission, we're cutting it to explode that energy outwards
Yeah.
and create destruction.
Yeah. Yeah.
Okay. And, they were doing a mathematical equation and concerned about setting the atmosphere ablaze, essentially. And is that a very real possibility? Because it sounded like the math made it a very real possibility.
I mean, there's something like the maths couldn't rule it out.
Okay.
It couldn't rule it out at the time. And probably, if we were in that position now, maybe we wouldn't risk it.
Yeah.
But we did risk it, and it didn't happen. Thank goodness.
Yeah. And so this is kind of what you're saying about, like, when we have an expected result and we don't get that, we've proven ourselves wrong, and that gives us a very interesting thing to look at.
Yeah. We're always looking to prove ideas incorrect. That's one of the more fundamental ways that science works.
Yeah.
We never, if we're really, really sure about something, there's no point funding any work that tries and proves it more correct. We don't have money just lying around.
Yeah. We got a whole department making sure 2 + 2 still equals 4.
Yeah, that's a really good point. Yeah, that's worth nobody's time. Right? But trying to prove things incorrect is great, because that leads us down a path of new science. If there's something that we thought was true that we realized through some experiment isn't quite true or is fundamentally untrue, that just unlocks so much more work for us to do.
Yeah.
And that's really exciting.
Yeah.
So that's always
business.
the goal. It kind of does.
Yeah, you don't have a job if you prove everything right.
Yeah, well, that's a really good point. But I don't know that that's a motivation. I think, I suppose different people have different motivations. Maybe people are looking for job security by proving things wrong.
Yeah.
I'm not sure.
True that. Well, they're probably anxious that the world's going to end.
And
so
maybe.
Fuck, I got to get it all done.
Got to get onto it.
Okay, so when it comes to us working on like energy for the future, nuclear is obviously a very possible and real topic. Are we essentially trying to recreate what a star is doing out in space?
In nuclear fusion?
Yes.
Yeah, because obviously nuclear fission, you can have like nuclear power plants.
Okay.
Which, so if we think about a nuclear power plant at the moment, it's like a nuclear bomb, but slower.
Okay, I didn't know that.
Yeah.
I thought we were trying to fuse.
We still are.
Okay.
Yeah. So there's kind of two options, So nuclear fission is not what the sun does.
Okay.
Nuclear fission is what a nuclear bomb does.
Yes.
Right? And then we can do that in a way that goes really quick and blows everything up. Or we can do it in a way that's a little bit slower, and we can use it to heat up some water instead.
Okay.
If we heat up water, it turns to steam, it drives the turbine, you've got electricity.
Right? Okay. So we're trying to make real slow bombs.
Yeah. And we're quite good at that.
Yeah.
So we've been doing that for a long time. We're also trying to do fusion.
Okay.
But fusion has a lot of really tough problems that it's tantalizingly close to being sorted out at the moment.
Okay.
And there's a lot of engineering details. But essentially, if you try and take some sun, right, and then imagine we take a little bit of sun and put it on the Earth. Well, the reason why the sun is able to fuse is because it's so big. And it's not big on the Earth, right?
Yeah.
We can't make something sun-sized. So instead, we have to compress it to pressures and temperatures well beyond what the sun has to do.
Okay. Yeah.
The sun has the benefit of being big and hot. We have to make something pressurized and hotter, well hotter than the sun. And the sun's pretty hot.
Yeah. What temperature is the sun?
Oh, don't ask me that.
Okay. But not quite as hot as what we're trying to do.
Yeah. No, that's right. So we got to get way hotter than that.
Yeah.
And imagine you've got something that's much hotter than the sun. Where do you put it?
Yeah.
Where do you put? How do you keep that contained?
You have a steady supply of like oven mitts.
Yeah, that's right. So this is called the containment problem.
Okay.
That we can make plasma, like the sun is plasma. We can make plasma that produces energy, but it's really hard to put it anywhere.
Yeah.
The thing about plasma is that it's electrically charged, and that means we can contain it with electromagnetic fields.
Okay.
But if you imagine,
You need a big magnet.
You need a big magnet. We're quite good at magnets.
Yeah. Okay.
When it comes to magnets, we've got superconducting magnets. We're pretty good at it. It requires like liquid helium. They've got to be extremely cold.
Okay.
But we can do it. We do it. In universities, we do it all the time.
Okay.
So it's good. The problem is, imagine this plasma as a collection of very high temperature particles.
Mm-hmm.
Some of the particles are going to be well behaved, and they're going to be relatively low temperature. They're going to be able to be contained by magnetic fields nice and easily. Some of them are going to be really, really, just like maybe 1 out of a million,
Mm-hmm.
really, really, really high energy, and they'll escape.
Okay.
And they'll smash into the walls of our container. This is inevitable.
Yeah.
You're going to get some that are escaping. And when they smash into the walls of the container, they'll do nuclear fusion to the container.
Mm-hmm.
And then the products of that are going to leak into the plasma.
Mm-hmm.
So it ends up being a big problem. So you need to make the chamber, the walls of this sort of plasma thing, stuff that when it becomes plasma itself isn't going to destroy the plasma.
Okay.
This is hard.
Yeah,
this is
yeah,
hard,
yeah,
hard,
yeah,
hard
yeah,
stuff.
yeah.
So that's mostly what people are working on. How do you make these walls work?
Mm-hmm.
You know, and we've used different things. We used like lithium, lots of tungsten, and trying to figure out exactly what to do and how to get it right is the job at the moment. It seems like, I mean, you know, it's a doable problem.
Yeah, okay, it is doable.
Yeah, we can make the hot plasma.
Yeah.
It's just where do we put it?
Yeah,
You know?
yeah.
I think we'll get there, but I don't know how soon.
Interesting. So, correct me if I'm wrong, but plasma is like the fourth state of matter.
Yeah.
So you have like a solid, a gas, and then a plasma.
Yeah, solid, gas, liquid, plasma. Yeah, there's a bunch of different states.
Yeah. Sorry, I
Yeah.
forgot liquid, solid, gas, plasma.
That's right.
That's an important one.
Yeah, I was looking up at the ceiling because sometimes you get, you know, those long fluorescent tubes.
Okay, yeah.
You know, that you get in offices sometimes.
Yes.
That's plasma.
Okay.
You know, so
and it's a magnetically charged.
Yeah, it's electrically charged. Yeah.
It's electrically charged.
Yeah.
Okay.
Gas, and it emits light.
Mm.
Perfect for like long tubes that kind of flitter and give you a headache. You know, so the sun's made out of that, but it's not this mysterious, crazy substance.
Okay.
You know, it's just charged gas.
Okay. Where does the electrical charge come from?
Well, I mean, atoms are made out of charges.
Okay.
You know, so where does it come from? It comes from the fact that electrons, which are in atoms, have a charge.
Yes.
That protons, which are in atoms, have a charge. Protons themselves are made out of small things that have charge.
Okay.
Why do they have charge is a different question. I don't know the answer to that. They do.
They do. They do.
Yeah.
They just are charged.
So you can imagine most atoms then are neutral because the protons have positive charge, but the electrons have negative charge. So they cancel each other out.
Yes.
But in a plasma, the electrons which are on the outside, we've ripped those off. And so what's left is a positively charged nucleus with some electrons around the outside.
Okay.
And so as soon as it's positively charged or negatively charged, as soon as it's charged, we can move it around with magnetic fields.
Okay.
We can contain it.
So in terms of what we're trying to do with nuclear energy, I've seen two different machines. One is like a big disc kind of thing.
Like a big donut?
Yeah, like a big donut.
Yeah.
Yep.
That's an ITER. Yeah.
Yeah, and so that is trying to fuse them or separate them.
Fuse. Yeah,
so
that's the big donut machine is a fusion.
And so that's spinning particles so fast that they're going to smash into each other and then nuclear fusion.
Oh, are you thinking of like a particle accelerator, like the Large Hadron Collider at CERN?
Well, maybe I was imagining the big donut thing in my head, but maybe I am thinking about a Hadron Collider.
Yeah,
because what's that doing?
That's also a donut, which is confusing, right?
Yeah.
But like big.
But a big donut, because that goes through a couple of different towns or whatever, right?
Yeah. That one. That's doing something slightly different.
Okay.
So in that one, which is huge, you know, let's talk about plasma and talk about like the size of a room.
Yeah.
Big, but we're not talking several towns worth.
Yeah.
What we're doing in that one is that we're not trying to establish a plasma using magnets. We're trying to use the magnets to speed up particles faster and faster and faster, smash them into each other, and see what happens.
So we're taking something that has either positive or negative charge.
Yeah.
We can then move it with a magnet.
So the hadrons,
We can use the magnets to speed it up, and then hopefully at some point it's going to collide with another particle that we have going super fast as well.
Yeah, I mean, you know, not hopefully. We are able to control it really, really well.
Okay, so we can
imagine
focus
like
them on each
one
other.
beam going one way, one beam going the other way, keep them slightly separate until they're fast enough, and then bring them together.
Okay, yeah, and we just move it Okay.
Yeah.
And that puts off a burst of energy
Yeah,
that we measure, but it doesn't sustain itself. Like it doesn't infuse and keep moving around.
that's right. And it's not designed to do that.
Yeah.
It's
Okay.
designed to, it's a big, long tube, superconducting magnets, moves really, really fast. And then at a specific point where we've got a bunch of equipment that's ready to do some analysis, we smash them together and all that equipment is ready to do an analysis.
Okay. And we're just measuring the energy that produces.
Yeah,
off that
energy,
collision.
but also like specific particles. So it turns
Okay.
out you get, say, 2 protons, smash them together, lots of stuff comes out, some specific particles are
Okay.
produced. Some of that stuff was made because it was inside the protons.
Mhm.
Some of it's made because it's like, products of the fact that you've just smashed 2 things together really, really fast.
Mhm. Mhm.
But we're looking for that stuff.
Yeah. Okay.
And because it's a probabilistic thing, things will be made with a certain probability, a certain chance. It's not sort of guaranteed each time. We're dealing with like quantum stuff here,
Okay.
and probability is a big deal. You got to do that thousands and thousands and thousands of times to
Okay.
really build up a picture of what's happening.
Mm. And so then when we talk about the other donut nuclear structure,
The nuclear one, yeah.
That is doing the same thing, but
Not really. We don't really have a beam. We have like hot plasma that we're just trying to keep still.
okay, so we're just trying to make a ring of plasma and hold it in a spot because that ring is going to produce heat, which is then going to heat the water.
Yeah.
Which is
well,
then
we've
going
got to
make
get it
steam.
from there. We've got to get it out a little bit so it can go heat water, right? Which
Yeah.
is another problem because you
Mm.
can contain it really, really, really well, but then it can't do anything.
Yeah. Okay.
So we've got to bleed it a little bit so we can get the
Okay.
energy out. But yeah,
Mm.
and
then,
it will heat water, make steam, drive a turbine. That's the ultimate
Yes.
goal. Yeah.
Okay. And then so now the third example that I've seen is essentially, fuck, how would you describe it? Kind of like a big sausage that looks like it has ring magnets around it that they're taking hydrogen or helium particles and they're fusing them together in the center.
Oh,
And that's giving off flashes of light and energy. And it's like super, super hot.
Yeah, that sounds more like a particle collider.
Okay.
Same kind of deal, trying to smash
Same
them together
deal,
and see what
but
happens.
smaller scale.
Yeah.
And because, was it, fuck, I can't remember who it was, but I was watching something on YouTube about it. And yeah, they had like this big sausage thing. They were talking about smashing helium together. And then they created another particle. They made essentially a plasma that these magnets were trying to hold still
Yeah.
in this sausage thing. And then it also put off something like tritium.
Yeah,
or
tritium.
Tritium.
Yeah, yeah.
Something like that.
Yeah.
That then they could actually store and then keep doing this reaction and store a whole bunch of the tritium, and then they could start feeding the tritium into smash with the helium again, and that would make an even bigger reaction. And what they were trying to do was make sure that none of the plasma particles touched any of the outside.
Yeah.
That it was just contained in the center. And they were able to repeat this constantly. And you were getting massive flashes of light, and it was like 10 million degrees or something on the inside.
Okay.
And so I was curious on, what is the difference between that type of nuclear energy
And like the donut.
and the donut one?
Yeah.
Like, because this one seemed way smaller, way
Yeah.
smaller.
Right. So it's just the shape of the magnetic fields.
Okay, so
That's
we're
all.
just experimenting, trying to find out what works.
Yeah, I mean that makes sense to me. Like a big kind of rod thing kind of works. Circles are really easy to do when it comes to magnetism. So you can imagine in the middle of it, you could have a very strong magnet, and then on the outside, you can sort of shape the magnetic fields really, really well. I don't see any reason why you couldn't do that. Maybe in like a long thing.
Yep.
It's just the shape of the magnetic fields.
Yes.
But ultimately, as you say, it's very, very similar. We've got a plasma in the middle. It's kind of the whole tritium thing is I guess it's tritium is really hard to find.
Okay.
And it's really necessary for fusion as part of a fuel. So I mean, it's not super hard to find. It's in seawater.
Okay.
So we happen to live on a planet which is perfect for doing this.
We've got a lot of water.
Fusion. We've got a lot of water. But it's a tiny, 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 tiny fraction of what's in there. So maybe they're looking at how to make more of it more easily. It's probably not cheaper to do that than it is just to get seawater. And when it comes to whether or not it's a renewable resource, that we've got basically heaps of it, heaps and heaps and heaps of it. But maybe they're looking for, hey, maybe we don't want to be combing seawater. Maybe we want to make it ourselves.
Yeah. Yeah, interesting. I wonder what it is about seawater that allows that element to exist. Is it?
It's hydrogen. Tritium is
So
hydrogen.
it is. Okay, so it is the hydrogen.
Yeah.
So it has nothing to do with like the salt that's in it or something.
No,
Is
it's
it because
water.
we make it out of fresh water?
Yeah. It's just, so what in water, which is H2O, there's the two hydrogens.
Yes.
But hydrogens come in different flavors,
Okay.
right? So a hydrogen which just has one proton is called hydrogen. A hydrogen there's one proton and one neutron is called deuterium. And a hydrogen there's one proton and two neutrons is called tritium. But they're all hydrogen.
Okay.
They're different isotopes of hydrogen.
Yeah.
And hydrogen, I think, is the only element where the different isotopes, we give them different names.
Okay.
So
what defines an isotope?
The same number of protons, different number of neutrons.
Okay.
And the different number of neutrons can mean that the atom itself has different properties. For example, we're made up of a lot of carbon. Most of that is carbon-14, which is 7 protons, 7 neutrons. But some of it is carbon-12. Hang on, I got it wrong the wrong way.
Okay.
Most of it is carbon-12, 6. Some of it is carbon-14, and the carbon-14 is very slightly radioactive.
Okay.
Like the balance of protons to neutrons is off. It's off balance. And because of that, it's very slightly radioactive. And so some of it goes away because it sort of radioactively decays. And then we replenish our carbon-14 by eating food.
Okay.
So you can tell how long it has been since something died by how much carbon-14 is left.
Okay.
We call that radiocarbon dating.
Okay.
So different numbers of protons and neutrons. Different numbers of protons are different names. They're different elements. Different numbers of neutrons are different isotopes. And why that matters is some isotopes might be radioactively stable and some of them might be not stable.
Okay. Where does the importance of radioactivity come in? Thinking about like sort of the nuclear fusion going on in the middle of a star, is hydrogen radioactive? And if not, when we set off things like a nuclear bomb, we're using things like radioactive uranium and plutonium and things like this. What is the importance of the radioactive properties, and why are we using things like uranium and plutonium as opposed to hydrogen?
Well, why am I using hydrogen bombs? I think there are hydrogen bombs.
Yes.
Yes.
So why are we using uranium and plutonium
at all?
Yeah.
Easy.
Okay.
It's easier to use. Yeah.
And the radioactivity makes it easier to use.
No, the radioactivity is just there. It's just a kind of a coincidence, kind of annoying.
Okay.
But it is there. So the uranium-238, which is the kind of uranium that you dig up out of the ground.
Yes.
Which means that uranium is 238 protons and neutrons. I think it has 92 protons, 238 protons and neutrons in total.
Okay.
That is radioactive in alpha decay. So it will emit these alpha particles. And then slowly, over a long period of time, it will decay into other things. So when uranium emits an alpha particle through radioactive decay, it's not uranium anymore, it's something else.
Okay.
That something else could be radioactive too. And so it decays and then turns into something else, and then it decays and then turns into something else, right? But the fact that it's radioactive doesn't mean it's good for these kind of like nuclear fission stuff.
Okay.
It's the fact that it's big means it's good for the nuclear fission stuff.
Okay.
But also the fact that it's big means it's not perfectly stable.
Yes.
So big things on the periodic table are radioactive, including uranium.
Okay.
But it's not, the fact that it's big makes it radioactive, and it makes it useful for fission, but it's not the fact that it's radioactive that makes it useful for fission.
Okay, so the radioactiveness is just kind of like a fuck. It's got this property, we're going to kind of work around it. It's really good for this, but we kind of got to get around this radioactiveness.
Yeah. It's something that happens. It's annoying.
And that is formed by as stars emerge and die and emerge and die and emerge and die, and more fusion happens.
Big explosions.
You end up getting to the heavier elements like uranium.
Yeah.
etc.
Yeah.
Okay, so
That's it.
all of the uranium that is essentially found on Earth, I can't imagine there's a lot of it because ISTA would have to go through so many cycles to be able to produce that.
Yeah, I think we've got
Makes it
like
rare.
a reasonable amount.
Okay.
You know where balloons like
Yes.
helium balloons.
Yes.
You go to the party store, it's like little shops on the road, get a helium balloon. That helium was made by the radioactive decay of uranium. So uranium was in a big cave underground, emitted alpha particles. Alpha particles capture some electrons just from the surrounding atmosphere and turn into helium.
Okay.
So all of that helium that we have from balloons and stuff is just from the radioactivity of uranium.
Wow.
I think that's fun.
That is very fun. I've never even never once even considered of linking the thought
Right?
of helium with radioactive uranium decay.
Yeah. So there's enough uranium that happens. I think it's also the radioactive decaying uranium that keeps Earth's core hot.
Okay.
Yeah.
Okay. So that those alpha particles have an energy.
Yeah.
Are
It's
producing
more like
some sort of energy.
Yeah, that radioactive decay produces a little bit of heat.
Yeah. Okay. And so that heat is it because that we use what I don't know if we my nuclear. I haven't been in a nuclear power facility in a long time.
Yeah.
So
fair enough.
But listening to things like is it the 3 Mile Island disaster?
Yeah.
There was a documentary put out about it and things like this. They talked about leaking radioactive particles from the core after a meltdown and things like this. And a meltdown, I am now similarly thinking of that as like, how do you contain the plasma?
Yeah.
The meltdown, because they talked about it, it gets so hot, but you haven't got the water cooling it down to be able to produce the steam and make the energy. So somehow it's burning through the vessel that was holding on to it, and that is your meltdown. I just never understood why we had to use something like uranium. I thought it was something to do with the radioactivity, but turns out that it's probably not.
Yeah, just a coincidence. We just need big things.
Yeah.
And the things have to be readily available. There's enough uranium in the crust that we can have mines and we can dig it up.
Yes.
So sometimes, I think there are some thorium reactors.
Thorium.
Which use thorium instead, which is very close to uranium on the periodic table. Molten salt thorium reactors, I think they are, which are meant to be a little bit safer, but they're a lot more expensive because it's harder to find thorium than it is to find uranium.
And so when we think of like a nuclear submarine, that just has a tiny little reactor of uranium or something that is emitting these alpha particles, which are exerting a little bit of energy enough to heat water to be able to produce electricity.
I don't think the uranium emitting alpha particles is what's providing that energy.
Okay.
I think it's the uranium being smashed by a neutron and then breaking up into two kind of even-ish size bits that's producing the energy.
Okay, it's that.
Yeah.
Yeah.
Because you can imagine uranium is really, really big. It doesn't really want to be big. It wants to be smaller. It's too big. And so one way it can become smaller is by letting a bit of itself go out, just sort of decay, or like leave. And that little bit is an alpha particle. And now it's smaller, slightly happier. You know?
Okay.
But if there happens to be a neutron flying around, which is just the right speed, smashes into the nucleus, it can fuse a little bit of fusion, forms uranium-236 instead of uranium-235, and the uranium-236 is unstable and can sort of form two kind of separate things, which are much happier. And then now that releases quite a lot of energy. So the radioactive decay releases a little bit, but this is a much more dramatic kind of reaction, releases quite a lot of energy. And crucially, 3 more neutrons.
Okay.
And so those neutrons can go and like do more reactions. That's what the chain reaction is. That's how it gets out of control and you get that meltdown.
Yes.
So if you want to keep things stable, you got to control those neutrons somehow. You got to soak them up.
Okay. And so when Oppenheimer and Einstein were talking about setting the atmosphere on fire, that is what they were worried about. How are they going to control those protons from creating a larger chain reaction?
I think at the time they were just worried about little combustion of oxygen. So they thought the oxygen would be on fire, and the oxygen would cause other things to be on fire, etc., etc.
Okay.
Yeah.
Okay.
Which didn't happen.
Thank God.
I'm not really sure how it would. Like I don't really know how that would work, the combustion of the atmosphere.
Well, that's the question I was
Yeah.
asking when I watched it.
It was definitely a concern,
Mm.
but I'm not really sure how that would happen. Normally, if oxygen is burning, it needs a fuel,
Mm-hmm. Mm-hmm.
something to burn.
Yeah.
When you set a fire in the fireplace, you're not just setting oxygen on fire.
Yeah. We got some carbon in there.
Yeah, exactly, right?
Mm.
All right, team, it's that time again. Sponsor advertisement time. Look, I know ads can feel like one song on repeat, but today's sponsors are the Bar Society and First Class Cocktails. If you've listened this far through the podcast, you already know that they're two companies that I personally own and operate. So hey, if you're rolling your eyes, at least roll them over to our websites and get ready to take your cocktail experience to the next level. Imagine this: First Class Cocktails premium bottled drinks paired with the Bar Society's crystal clear ice. It's a match made in cocktail heaven. Whether you're hosting a dinner party, impressing guests at a wedding, or just treating yourself to a well-deserved drink, these two brands will bring you everything you need for a flawless pour. First Class Cocktails delivers unbeatable flavor, while the Bar Society adds the perfect touch of elegance with slow-melting, pristine ice. Why settle for ordinary when you can create extraordinary? Head to firstclasscocktails.com and thebarsociety.co.nz to order today. Together, we'll elevate every sip. First Class Cocktails and the Bar Society. The perfect pairing for your perfect pour.
And so, I guess with nuclear fusion in a star, then you don't require oxygen because the fire on Earth requires oxygen.
Yeah.
Well,
it's not fire in a star. It's not combustion. It's fusion.
Okay.
It's a different thing.
Okay. So that's the distinction.
Yeah.
It's not a burning ball of fire.
Yeah.
It's a ball of fusion.
It's kind of hot and it's glowing and it's going, so it's like pretty close to burning. So we'd like to call a star burning, but that's more of a metaphor.
Just our little monkey brains have to find a way of wording it so it makes sense.
Yeah. It's not a literal description.
Yeah. It's a nuclear fusion reactor, but we call it a burning ball.
Yeah. Big burning ball of fire. There's no fire there. Actually, it might be a little bit of fire. It depends on what fire is.
Yeah, and I guess, if there just so happens to be a planet somewhat like Earth that has some trees on it that gets close, it'll make a little bit of fire.
It would make some fire. Yeah.
With the
planet
energy.
would be the fuel.
Exactly. Exactly. I wonder how often that happens. Things falling into the sun and getting burned up.
I wonder too.
Introducing more energy.
Because obviously, the reason why we don't fall into the sun is because we're going sideways really fast. But if something happened to come towards us, some kind of errant planet or something, and smack into us and stop us going sideways real fast, well, we'd spiral in.
Yeah, okay. Yeah. And we would end up being swallowed up.
Yeah, potentially.
And then the sun expansion's the least of our problems. It's the fact that we've stopped.
Yeah.
We've stopped moving.
Yeah.
Is that a very real possibility?
I hope not. You know what? I've got other problems to deal with.
We got theremins to build.
I'm not interested in finding more things to be anxious about. That's fine.
What is really the biggest concern in the physics world about the end of the planet? Because I bet people speculate about different endings and time frames and things like this.
I mean, that's almost more of a political question.
Okay.
Really? What are we going to do to ourselves? Are we going to blow ourselves up? Are we going to do climate change so hard that we can't live anymore? Is something else going to happen? I'm sure there's plenty of physicists who have strong opinions on it, but I doubt those opinions are based in physics. I think they just have those opinions because they're people living in society, right?
Yes. Yeah. And we're all an amalgamation of all the different shit we've heard and what we want to believe.
And it's not like physicists are some enlightened beings, that their opinions are all right all the time.
Yeah.
They probably know a lot about their specific field, and I bet they think they know a lot about other things, and maybe they don't. So I wouldn't take the political opinions of physicists with too much credence.
Okay. Good to know.
Good
to know.
That's right. They're just people.
Well, exactly. We all are. We're all just people. That's like, we're sitting here in Panacea surrounded by a sea of whiskey.
It's pretty cool.
Yeah, it is. It's quite nice to look at.
I really like it here.
Yeah. But like people that know a shitload about whiskey, don't necessarily know everything about vodka or gin, even
Sure,
though they're
or-
somewhat starting from the same thing.
Yeah, or nuclear war.
Yeah, exactly.
Right? Yeah. So yeah, that's a really, really good point.
Yeah.
And I'm sure there are plenty of whiskey people who are passionate, interested about whiskey, and they probably would say, "Oh, don't ask me about gin." And
Yeah.
I'm sure there's plenty of passionate whiskey people who have unfounded and unreasonable opinions on gin.
Yes.
Yeah,
for
it's
sure.
same.
Yeah. So now I kind of want to get a little bit far out there
Okay,
in terms of
good. Yeah, let's do it.
alien life.
Oh, okay. Yeah, good. Go on.
Yeah.
Yeah.
So I have always kind of believed that alien life has to exist because it made us. As our planet formed,
We're here.
all of the shit came in.
They
All
came
of the
in.
particles that we're made out of came from outer space.
Exactly.
I feel like it is just stupid to assume that has not happened somewhere else. We're special.
I think you're exactly right.
Okay.
And I do think that we want to turn that kind of instinct into, well, what can we do to actually test that? What is it that we can do? And one of the things we can do is look for life in places. One of the things we can do is kind of map different solar systems and see what planets look like in those solar systems. One of the things we can do is understand more about that beginning of life, abiogenesis.
Okay.
And those different chemicals, where do they come from? How are they made? How do they end up in the same place? And what do they do together once they're there?
Would you like a top up?
Sure.
Sorry to interrupt.
That's okay. And so the science of thinking about whether or not there's alien life is that. It's kind of understanding more about what those kind of conditions are for the start of life, which we don't know comprehensively. We're still learning a lot more about that. Kind of the conditions out there for different places, are those conducive to life? And we don't know enough about that yet. But we're starting to build up this picture where the chemistry that begins life seems pretty doable. All chemistry happens because of electromagnetic forces between the particles and the molecules. And it turns out you just have enough of these particles, which are kind of everywhere, together long enough, they can form proteins and they can form, things that are complicated molecules that eventually make life. And they need the right conditions. And as we look more and more at different solar systems, the difficulty there is in finding smaller and smaller planets. So it's really easy to see big planets. It's really easy to see Jupiter-sized planets.
Yes.
And I'm sure you probably would have seen in the news sometimes super Earths. Found. You hear that. They're called super Earths because they're big. And it's easy to see big things. It's harder to see small things, right? But it seems like there are planets. The planets have water. That should be enough.
Have we found any planets that have a tree or any sort of
No,
organic life?
and we do know what to look for.
Okay.
We do know what to look for. So we're looking for something called biomarkers, which are when we look at life on Earth produces certain molecules, certain chemicals, and those chemicals have a certain interaction with light that we can detect. And so we are looking for those things. One of those is oxygen.
Okay, yes.
Because oxygen is really reactive. If you've got some iron lying around, it will form rust. If you've got some fire, it will burn. Oxygen is really reactive. So if you leave a planet with oxygen sitting around long enough, well, the oxygen will go away. Eventually. It'll be absorbed into rock, or it will be part of chemical reactions or something, but it won't be O2 oxygen gas in the atmosphere forever. So the reason why we have oxygen gas in our atmosphere is because we have living organisms that produce it.
Okay, yes.
Right, which are plants and algae, etc. So if you see oxygen in the atmosphere, it's probably because something alive put it there.
Yeah.
So we're looking for oxygen, but hey, life on Earth produces oxygen. Maybe life somewhere else doesn't produce oxygen. Maybe it's something different. And so there are a number of things we're looking for that...
it's pretty rich to assume that if there's life out there, it has to be like us.
Yeah, the thing is, our life, a lot of our chemistry, is based on going back to the periodic table, pretty small things on the periodic table. If Earth didn't have uranium, sure, we wouldn't have nuclear bombs, but we could still exist.
Yeah.
We don't need uranium to live and evolve and function or anything,
Mm.
right? So uranium isn't necessary, nor is gold. Iron's pretty necessary. We need that in our blood,
Yeah.
right? For
Yeah.
hemoglobin. But most of us is carbon, oxygen, hydrogen. Carbon, oxygen, and hydrogen.
Oh, yeah.
Most
yeah.
of it,
Yeah.
right? Pretty low down on the periodic table. So probably any other life that's formed, it might not have DNA and it might not look exactly like us, but it's probably carbon, oxygen,
Yeah.
hydrogen.
It's got the basic building blocks of life.
Yeah, it's not a coincidence that we breathe oxygen.
Mm.
We couldn't breathe nitrogen and live in it. We are breathing nitrogen right now. Most of the atmosphere is nitrogen.
Yes.
And we don't do anything with it. You can't burn nitrogen.
Yes.
You can burn oxygen. Right?
Okay. And so is it the biological organisms on a planet producing things like oxygen? Is
Yeah.
that what creates an atmosphere to be able to contain the oxygen? Because if they just produce oxygen with the just kind of float out into the nothing.
Well, it needs an atmosphere.
Yeah. And so what is an atmosphere normally made up of?
Just gas.
Just gas.
So like our atmosphere is gas. The reason why it's here is because it's trapped by the Earth's gravitational field.
Okay.
It's keeping it in.
Yes.
So it needs to be the right size.
Yes.
Something that's too small won't have a gravitational field strong enough to contain gas.
Okay.
Right? Like the moon. Mars is strong enough to contain gas. And once upon a time, it had an atmosphere, but it lost it because the sun is awful. The sun is deadly. It's throwing out all these particles all the time, and it's scoured Mars clean of its atmosphere after long enough. So it's big enough, but it doesn't have a magnetic field like Earth does because its core cooled and solidified. And so it couldn't protect its atmosphere from being scoured absolutely clean.
Okay, so having a hot core is a key part of being able to sustain the gravitational force
for something Earth-sized. Yeah, because we're not too big.
Yeah.
So I think even if we were bigger, the atmosphere would be scoured clean eventually. So Venus has a hot core and it's got quite a thick atmosphere.
Okay.
Jupiter's a gas giant, but it's just a big atmosphere.
Yeah,
right? It's just real thick on the atmosphere.
Got that thick atmosphere.
It's got a thick atmosphere. You look at it and go, oh my god,
hey, that's a chunky atmosphere you got
tempestuous.
there.
Yeah, that's right.
Oh, crazy! And so, I imagine, life.
So
probably,
so life will change the atmosphere, but it won't make it.
Yeah. Okay. You need an atmosphere to have life, but it's not the life that makes the atmosphere.
Yeah, it'll change it. Yeah, it'll alter it in ways that we can detect.
Yeah.
Right?
Okay.
But it won't make it be there in the first place.
Yeah.
Yeah.
And how have we detected any of these biomarkers?
Not yet.
Not yet.
It's hard. Sometimes, we've had a couple of exciting near misses.
Yeah.
We go, we've detected some biomarkers. It's pretty exciting, but the biomarkers are a little bit niche. They're not like oxygen. They're like a more like a specific kind of molecule.
Yeah.
And we look at it a little bit harder, and it falls apart. It's strange. There is this tension where, as I said before, the more we learn about how life started and the requirements for life, and the more we see that those things are common, the more we expect, well, life should be pretty much in a lot of places. They're looking really hard. We haven't seen any yet. And it's getting more and more surprising that we haven't seen any yet. And our tools for looking are pretty sophisticated. We're not just sort of staring in a telescope and hoping to see a spaceship. We're analyzing the atmospheres. Think about the Earth. The atmosphere is a tiny, skinny little thing around compared to the rest of the Earth. We're analyzing the atmospheres of planets in different solar systems. That's insane.
Yeah.
Our capabilities are pretty good.
Yeah.
It's very impressive what we can do. And still nothing.
And that makes me feel like, it's rare but not impossible.
Yeah, it's got to be. I mean, my personal belief, it's got to be somewhere.
Yeah.
We keep looking, we'll find it eventually.
Yeah.
We might find it here in our solar system. Maybe in the moons of Jupiter. So Europa in particular has a water ocean.
Okay.
There's everything on Europa, which is a moon of Jupiter, everything that should possibly need life, but it that life should need
Mhm.
to like live.
Yeah.
Doesn't guarantee it, but it's kind of the potential is there.
It's there.
Yeah.
And we haven't been able to get so deep into the ocean that we've noticed a fish.
Well,
Because
it's
would sea life put off the same biomarkers as what a tree or a person would?
it could do.
Okay.
We like it's a big question of interest. People are looking really hard, but we kind of need to go there and look. It's cold. It's ice,
Okay.
right? So it's got ice on top.
Mhm.
But a particular property of water is that ice floats. Water ice
Yeah.
floats.
Yeah.
You know, not every kind of solid does that. Normally, solid things are heavier than their liquid equivalent, and they
Yes.
sink.
Yeah.
But water floats, and so having a water ocean is great for life because it can freeze on top, and then underneath can be liquid.
Yeah, and
And-
still sustain life.
And can be warm because of tidal forces. Far away from the sun, but it's close enough to Jupiter that it can sort of have quite a lot of energy. Right?
Mm.
So we can see the ice, we can't see under the ice.
Yeah. Okay. So tidal forces and warmth, is that coming from the friction
Yeah.
of
Yeah,
the
yeah.
movement
Like
back
squeezing,
and forth
yeah.
under the ice,
Yeah.
and that generates a warmth
Yeah.
that allows life to potentially form?
Yeah.
Because
Yeah,
I can't remember what I was watching the other day. The documentary about the Titan disaster, the billionaire that
right.
made the carbon
The-
fiber hull, and
yeah.
fucking
Yeah.
gone. Sorry, cuz you're out.
Oh, it's just so brutal.
Oh, a rough way to go.
I
Rough
mean,
way to
is
go.
it?
Well,
it
it
was
would have
just
been quick.
It would have been quick.
Would have been quick, but watching the documentary, like they had done all these experiments with the pressure
Yeah.
on the carbon fiber, and they put all these acoustic sensors in it to hear if any carbon fibers snapped, and it starts off playing the video of the final voyage,
Wow.
and essentially you hear,
Jesus. Okay.
and that
That,
would have it's going.
that's terrifying.
It's going, and
Imagine
you're not
being
making it to the top.
the one person on the boat who knows what that means.
Yeah. It was the main.
It's just like, what is that? What is that?
Yeah.
And you get the one guy who's like, oh.
Yeah. Spoiler alert for anyone that's listened to this. You haven't seen the documentary?
No, it's okay. I'm willing to be spoiled.
Okay. So they
I've given
had
my
done
consent.
a lot of tests
Yeah.
on this carbon fiber hull, and it essentially never passed.
Well, that's pretty dumb.
Super dumb.
That's dumb.
And every engineer or technician that, one of the pilots refused to pilot it. He was like, it's not safe. I'm not taking myself or anyone down in it.
Yeah.
So the boss, he was like, well, fuck you, I'll do it. And then the lead engineer, he was like, we don't know what perfect looks like, but we know it shouldn't look like that.
That's a really good phrase.
Yeah, I thought it was genius.
I like that a lot. Yeah.
And he was like, well, fuck you, bro, you're out too.
Yeah.
And so anyone that questioned him, he pretty much just axed them.
That's stupid.
But moronic.
Why are you hiring smart people? Why have an engineer if you're not going to listen to their engineering expertise, right?
Yeah, exactly.
Yeah.
But he wanted to be this, he wanted to be like a Jeff Bezos and Elon Musk, just pushing the boundaries and claiming something.
Well, he didn't. He exploded.
Imploded.
Instead.
Yeah, along with a few other billionaires.
Yeah, that's right.
But
hard to have sympathy for that kind of attitude. I mean, I feel bad for the people who died, but
for sure.
Yeah,
for sure.
Also, don't go down in the boat.
Yeah. I mean, it's clearly said in the waiver this is an experimental craft. Death is possible, and they were like, "Sweet bro, I got time." It was ridiculous. But anyway, they had done all these tests. It turns out that it really wasn't going to work.
Yeah.
And to be fair, impressed with how many times they actually went out in it. Because, one time they went down, they heard a whole bunch of pops. He came back up, they looked at the hole, they found that it had started cracking. So they ground it out, saw how deep the crack went, and just went and rebuilt it. And then they did some scale model testing, and that failed. And they're like, oh, well, fuck it, we're going big anyway. And they just started making the bigger one. It was just really more ego than science.
Yeah.
It's just, he wanted to be one of these Elons, and had the thing that kind of, I think, is the difference that helps the ego play such a big part is someone like Jeff Bezos or Elon Musk. They kind of didn't start from massive amounts of wealth.
enough,
they started with enough,
but not
not
what they
generational.
have.
Yeah.
Is that yeah?
Yeah. So I mean, they still had to build everything from the ground up.
Sure.
Whereas this dude and his wife
Mm.
had come from generational wealth,
Right.
where money had never, ever, ever been an obstacle that they ever had to figure out. Like, so the Stockton Rush, the dude who was behind Ocean Gate, he could trace his family line back to 2 signers of the Declaration of Independence.
Oh, wow.
And so, had
Yep.
been an important person for generations. And his wife, her family, so they died trying to go to the Titanic, right?
Oh, yeah.
2 of her family members died on the Titanic.
Okay.
And then other family members of hers started household names like the Macy's department store and things like this. And so they just came from where massive money could mingle with all of these people that had the same type of money, but didn't actually have any, career.
Yeah, I take your point.
To work on,
They never needed an expertise.
They never needed an expertise. Like, he went to, I think it was Princeton, and studied aerospace engineering, and he got like D's, C's, and F's.
Right.
Like, he was not a leader in his field. Yeah. He wasn't a revolutionary thinker by any stretch of the imagination. He just, wanted to do some cool shit.
You don't need to be.
Yeah.
Right?
He just wanted, it was bizarre, but he wanted to be one of these people that was groundbreaking. And he did make some really cool points. He talked about how he watched Star Trek and Star Wars, and he wanted to be an astronaut and see all this alien life out there. But then he realized that a lot of the alien life, it's actually under the sea.
Yeah.
And so if you get down it,
that's true.
And I'm like, that's probably the smartest, most insightful thing you've said this whole fucking documentary.
Yeah.
It was so true. And I am a believer that, life starts in liquid. It starts in the ocean.
Yeah, of course.
That's where you have your algae and everything, and there's so much more of the fundamental elements that can sustain life. And fish, and then as tectonic plates smash and mountains start being formed, suddenly there becomes more land and not as much water. And so that's where we sort of evolved to be like, oh, well, there's this land thing here now, might as well utilize some of it.
Life likes to fill things up.
Yeah, exactly.
Yeah, if there's some space, it'll get there.
Yeah, if we're, like you're saying about one of Jupiter's moons, if it's all water, well, the only spot you can hang out is in the water.
Yeah.
But eventually, if there's some sort of volcanic activity and a hot core and whatever, and some mountains start to be pushed out, well, something is going to fill that void and evolve to live on that piece of land as opposed to in the water.
Well, true. But I mean, to your point, it doesn't need to.
No, exactly.
You don't need land.
Yeah.
I guess we needed land. I guess if we had, I don't know, done what the whales did and go back to the ocean, would we have opposable thumbs and the ability to build things? Maybe, maybe not. But life doesn't need land.
Yeah, 100%. That's so true. So true. Yeah, life doesn't need land. And so I kind of believe that, something like an ocean world, there's a very strong possibility that there is life under there.
In water, if there's stuff and there's other stuff, water gives the opportunity for that stuff, like I'm just thinking of molecules and that kind of thing, kind of mix and combine, and for stuff to happen. We talk about a primordial soup. Primordial soup is just like it's just an ocean, right? It's just water. It's just a place for like stuff to go and happen, right? So land on its own, I mean, that's, Mercury is land on its own.
Yeah.
Mars is land on its own. It's nothing's there, right? You need that ability for stuff to come together and combine. And if you think about life on land here, all we are is like sacks that are keeping in wet stuff. We're still wet stuff. We've just developed these kind of like bags that can fit around the outside to keep all of our wet stuff in, right?
And when we get nervous, it leaks some of
it
the wet
leaks
stuff
a little bit. We get sad, it leaks a little bit. We drink too many cocktails, it leaks a little bit. So we're just sacks of chemicals. That's all we are.
Yeah, the old chemical meat sack.
Right, it's just a chemical meat sack.
That's great to think about. I love that sort of phrasing. But I kind of believe, the scariest thought I've ever had in the frame of does life exist elsewhere is Big Bang, there was something.
That did it.
Yeah, there was something that did it, and that made everything else.
Yeah.
And we're existing in the everything else.
Yeah.
Looking at all this shit, being like, oh, there's all of this
Yeah,
shit.
it's everywhere.
Yeah.
Yeah.
But there was a starting point.
Yeah.
At some point, which we don't know. We don't know what the starting point was.
Yeah.
On the very rare chance that life on this planet is the starting point.
I take your point, though. When it comes to life, it had to start somewhere.
Yeah, it has to start somewhere, and maybe we
maybe
are the
here.
start point.
Yeah.
That eventually, when our planet dies or gets smashed into by something else,
maybe it'll spread then.
it's going to spread our stuff, our meat sacks
elsewhere.
elsewhere.
And it just needs a little bit.
Yeah.
And then just needs some algae, some bacteria or something. Well, I've got an interesting thing for you.
Okay.
In that respect.
Yeah.
And that is space at the moment is pretty cold. Right? It's about 4 Kelvin. It's very cold.
Yeah.
But it used to be smaller.
Yes.
And when it was smaller, it was hotter.
Okay.
Big Bang, very, very small, very, very hot, very, very dense. Somewhere in between, there must have been a point where it was about this temperature.
Yeah.
It was
throughout the whole universe.
A temperature specifically which allows liquid water to exist.
Yes.
So the ambient temperature of the entire universe was somewhere between 0 Celsius and 100 Celsius, which means on an asteroid floating around in space, liquid water. On planets everywhere in the galaxy, liquid water. Which, I mean, maybe there hadn't been enough time for suns to explode and for interesting stuff to be made yet. But if liquid water is what you need to allow that advanced chemistry to happen, maybe it's at that point, long ago, when the entire universe could have liquid water, that the beginnings of life started to just sort of happen everywhere.
And we all would have been closer.
We would have been closer, probably still pretty far away.
Yeah.
But closer, certainly. And that maybe how life started on Earth is that an asteroid that had a little bit of that sort of chemistry start to happen on it. Once the universe expanded more, it got colder, all that stuff froze. Just because it froze doesn't mean it's gone. It's frozen. Smashes into a young Earth, and then life. Maybe that's where it came from.
Yeah.
And if that's the case, the seeds for life could be everywhere.
And it was
an exciting thought, I think.
The seed of life, that's an interesting, a good way to put it, because the seed is where a plant starts.
Yeah.
But then that plant produces seeds.
Yes.
Which allows it to seed elsewhere.
Yeah.
We're spreading the seed of life throughout the solar system. Maybe we are the byproduct. We are the seeds.
Yeah, I mean, there's nothing different about us than everything else. We're able to kind of think about thinking and think about
thinking,
and think about, I don't know, destiny and that kind of thing in a way that maybe a rock isn't, and that could be a fundamental difference between us and rocks. We've got awareness of ourselves, but we're still just part of the universe like a rock is. We're all made out of stuff that was born in a star just like a rock is. The difference between us and the rock is that we can kind of think and move and change in a way, and and reflect in a way that's very different. And so us spreading life is just the universe doing stuff. We're not separate from the universe. What we do is the universe doing things. There's a kind of element of determinism in there, like a lack of free will, that I don't necessarily agree with. But yeah, maybe that's how life gets places. It evolves thought, and then it goes places and does things. Who knows?
Yeah, well, I guess that's a there's almost like two different ways of looking at it. We either life gets spread throughout the universe due to disaster, or it gets spread because of curiosity.
Yeah, true.
And it's up to us to go to the other place, as opposed to waiting for something to smash into us and send us to the other place.
I mean, I think it's pretty inevitable that as soon as that we can get somewhere, we'll probably go there.
We'll go there.
We'll go there.
Yeah.
I think, we're that kind of species, that kind of organism.
Yeah.
We can go somewhere, we'll go there.
Yeah,
For better or worse.
yeah, well, that's exactly right.
It doesn't matter if it's better or worse, we'll be there
Yeah,
as soon as we can.
yeah, for sure. When you, like, we very, very briefly touched on quantum mechanics and physics, and you said that a lot of it is based on probability.
Yeah.
So is this like the Schrodinger's cat principle, you know? Is it dead? Is it alive? Both realities exist until we observe it.
That's right. So Schrodinger's cat was a little thought experiment that was made by Schrödinger and Einstein because they were really uncomfortable with this idea of a probabilistic basis to nature.
Mhm.
Einstein came around on it. Like, he realized, it's just kind of what it is.
Yeah.
I think they were convinced after a little while. But they tried to they put together this thought experiment to describe the absurd nature of
Mhm.
this. So they say, where you've got a radioactive atom, it radioactively decaying like uranium. The point at which it does decay, it's going to decay.
Yes.
But exactly when it will decay is a quantum mechanical process.
Okay.
It's going to hang around as uranium for a little bit, and eventually it'll release its particle. And that kind of mechanism is described by quantum mechanics.
Okay.
So you can't know exactly when it's going to decay. So we'll go, okay, when it decays, we'll have a little sensor, releases some poison in a box. What happens to the cat? Is it alive or dead? And they talked about, well, it'll be alive and dead simultaneously until it's observed, but that kind of presupposes this notion of observation being a person has to look at it.
Yes. Yeah.
Right?
Yeah.
But that's not right.
Does it have to be a person? Could it be a dog?
It could be, could it be air? Right? And what does look at it mean? When you open a box and look at it, right, photons are coming from the cat to your eyeballs. There's an interaction. There's a particle interaction there. So as soon as there's some kind of interaction of a quantum system with other quantum systems, remember, like, all systems are quantum.
Yeah.
When you get down to it, all atoms and stuff, they're all quantum systems. Eventually, there's what we call entanglement, where the effect of one system has an effect on something else, etc., etc. And that really is what observation is.
Yes.
So opening and looking at it isn't observation. What is observation is atoms interacting with each other. And then that is like the basis of reality, if you like.
Okay.
So it's not that the cat is alive and dead simultaneously until you look at it. But at first glance, that is what the maths kind of is trying to say is going to happen.
Yeah. Okay. And so if, like you say, everything is part of this quantum universe.
Yeah.
When we reference back to life elsewhere, the probability that it exists elsewhere is not zero.
Oh, I see what
Like,
you mean.
there has to be some sort of probability
Yeah.
because the whole everything is made up of this quantum shit.
Yeah.
There is definitely a probability that something else exists out there.
Yeah. I agree with you. Don't get caught by this idea that just because it's probabilistic means anything could happen.
Okay.
So I guess, like, I might be being a bit pedantic here, but sometimes they say, well, it's probabilistic, so it sounds like, well, anything could happen, but really we're talking about, like, it's 50% this, it's 50% that.
Yeah, okay.
It's one or the other.
So the probabilities are 50-50.
Yeah.
Yeah, it's not like an infinite amount of possibilities.
Yeah, so
We can't see the dead or alive.
Yeah. And then when we're
Life.
talking about quantum mechanics is a useful thing to think about when you think about, like, chemical reactions. So if you're thinking about what probability is there that chemicals have reacted together elsewhere to form, like, the building blocks of life, some peptides and some proteins and that kind of thing, that can be a quantum mechanical question. But whether or not there's life elsewhere isn't really a quantum mechanical question, right?
Okay.
It's sort of out of the scope of quantum mechanics to worry about.
Okay, so that's more of just our human curiosity and ego wanting to either be the only life or wanting there to be life somewhere else.
Yeah, I
Not really
wonder about that.
The quantum mechanics of if it's a possibility.
Yeah.
Interesting.
Like, I think there'll be life somewhere else, but it doesn't really matter. It doesn't matter what you think until we find it.
Yeah.
Right? It matters, politically, like, are we going to fund experiments to try and look,
Hmm.
you know, and I would, if I had the purse strings, I'd fund them. Fine.
Yeah.
You know?
Yeah.
Right? Yeah, obviously. But you know, it's an interesting question until it is real.
Yeah. Yeah.
Right.
Yeah. And so, do you think we're probably going to venture out to another planet ourselves before we actually find life on another planet elsewhere?
That's a good question. Maybe, you know, it's looking pretty grim for the life of searching for life.
Mm.
You really thought we'd have found something by now, and
Yeah.
we haven't.
Yeah.
So yeah, potentially.
Yeah. Yeah. So maybe we are the first
Could be.
part of life. We are the first intelligent,
Yeah.
oxygen producing life.
Well, there's something to that as well, where occasionally there'll be big gamma ray bursts. And so the Milky Way galaxy went through a couple of large-scale gamma ray bursts from different kind of stars decaying and stuff. So stars blowing up is a very complicated thing.
Mm.
Sometimes it can just make sort of dust and gas, and sometimes it makes massive amounts of radiation. So there looks like there was a couple of times in Milky Way's history where that, if there was life, that gamma ray burst might have wiped it clean.
Okay.
Right?
Yep.
And so we're not here very long after the latest one.
Okay.
You know, a couple of billion years or so, but
Yeah.
still, it's not that long since the latest one. So maybe there was bacteria or algae or something on a planet or asteroid somewhere that didn't survive the latest kind of gamma ray burst,
Yep.
and maybe we're the first intelligent life that has arisen since. It's perfectly possible, but it's all maybe.
Yeah.
You know, it's all maybe. And so the answer to that maybe is not to not worry about it, it's to keep looking.
Yes.
You know, it's a big open question. It's exciting to have these big open questions. You know?
If you were if Earth received like another big gamma burst, would it maybe cook everything that was hit by that, but there would be a small isolated spot on the other side of the planet that gets untouched?
No, it would go straight through.
Oh, okay, it just penetrates straight through.
Yeah.
You're all fucked.
Yeah. Yeah.
Oh,
Fully
dude.
wipes out. It could happen at any time. And of
Mm.
course, a gamma ray is light. So that's
Okay.
traveling at the speed of light. And if something's
Yes.
traveling at the speed of light, there's nothing faster than it. So we will get no warning.
Yeah. It'll
just happen.
Yeah.
Could happen at any time.
Yeah.
It probably won't.
And we
Go.
wouldn't even know about it, really.
Nope.
It would just cook us.
Gone.
Dead.
Yeah.
See you later.
Yeah.
Mm.
Entirely possible. Extremely unlikely.
Okay.
And again, not worth worrying about.
Yeah.
Right?
Okay.
I'm worried more about traffic on the way home than I am about dying from a gamma ray burst, right?
I'll text my missus and make sure she's not packing the bags already.
Yeah, that's right. There's nowhere to go. So don't worry about it.
Come on, Elon. Get us to Mars quickly.
Yeah,
and then we perish halfway.
Yeah, it wouldn't help.
No.
If we get wiped out, Mars does too.
Yeah.
Whoops.
Ah, fuck. What do you think if we were to settle on another planet, what would be the best option? We build a little, dome to be able to contain ourselves in and kind of live in a dome city, or would we do something ridiculous like what Elon's talking about, terraforming and setting nuclear bombs off on the polar caps?
Yeah, well, I mean, maybe we'll learn more about terraforming, get good at it, and actually manage to do it.
Because I imagine it takes a long time. You got to set a couple of bombs off and then wait like 1,000 or so years, maybe more.
And also, Elon Musk is not a scientist.
No.
So when he talks about that stuff, he's talking science fiction.
Yeah, okay.
Yeah, maybe, okay. The scary thing is he might actually do it. But it doesn't mean it's going to have the effect that
the desired
he thinks
effect,
it will.
Yeah.
So I think it will be a dome city. I think we'll establish a permanent presence on the moon. I think that'll be like a dome thing. I think we'll end up on Mars. That'll be a dome thing. And I also think it'll suck. I also think it'll be awful to live there, you know? So I think,
you're going back to the Stone Age on a foreign planet.
Yeah, and it's just what you want to go for a walk? Where?
Yeah. Walk up and down this tunnel.
Yeah, and if you go outside in a big spacesuit, go for a little walk out, there's rocks.
Yeah.
That's all there is. It's just rocks.
Yeah.
So I think when we end up there, it might be for like scientific missions.
Okay.
Like we'd like to dig up and see what's there. I strongly doubt that it would be a big colonization push.
Mm.
You know, I'd love to visit Mars. If that was a possibility, I'd do it. Would I live there? Would I live in Antarctica?
Yeah.
You know?
But that's exactly right.
I don't think I'd live in Antarctica.
Yeah, there's spots on our own planet we don't even want to live.
Yeah.
Why would we want to go to a barren other planet?
Would you live in the middle of the Saharan desert in just a dome when you could not do that?
Yeah.
You could live in Auckland if you wanted to, and go out to bars and that kind of thing. I think I'd rather do that.
Yes. Yeah, for sure.
Yeah.
Oh, great. This has been such a great conversation. I really
thanks,
appreciate
man.
your time.
Yeah,
This
I've had a
has been
good time.
fascinating.
Yeah, I appreciate it.
We will have to do this again because I still have so much more questions and would love to get more in depth about so many different things. So I would love to do this again on a later date.
We've talked about some big stuff.
We have.
Yeah.
We have. And I think
has
I'm
been
probably
fun.
going to have to listen back to this to be like, make sure I understood the concept.
Yeah, well, hopefully I explained it well.
I think you did.
We'll see.
Yeah.
I had a good time.
I'm
That's
glad.
fine. Yeah, it
I'm
was
very
good.
glad you had a good time.
Yeah.
Thank you very much for coming in. Appreciate you very much, Lee. And we will 100% do this again. Talk about some more big things.
Hey, that's exciting.
Maybe some more things to freak everyone out.
Yeah, I wouldn't mind doing that.
Yeah. Awesome. Great. Thank you very much for your time, Cairan.
Okay.
Thank you for everyone that was listening. Enjoy your
Goodbye.
day. Ciao.
That's it for this week's episode of the Breadcrumb Mojito podcast. Follow us on Spotify, YouTube, Instagram, and TikTok at the Breadcrumb Mojito podcast and look out for next week's episode.